All right.
I see it's 2:14, so I wait another 30 seconds or so. And I see we're now at 72.
So people who want to ask questions, just raise their hands or put questions in the chat.
Best is to put the names in the chat or say that you have a question, or maybe even formalize your question. And then one of the chairs will, or co-chairs will take care of that either during the talk or at the end of the talk. So that's better than raising hands, because we cannot keep all the people in check. There's too many people.
So via the chat.
I think so.
Yeah.
Or Slack.
Okay, let me start. Welcome everyone at the 76th, unfortunately not your ordinary, Netherlands Astronomers Conference. The Royal Netherlands Astronomical Society Board decided we try another format this year. 5 short, plenary, online afternoon sessions. During the past months, the Society's structure was evaluated by a committee of young astronomers. This committee stressed that the Society should concentrate on its prime goal, building, strengthening the astronomy community in the Netherlands and Flanders. During the business meeting next week, Thursday, we shall discuss the recommendations of the evaluation committee further. Concerning this conference, an ad hoc scientific organizing committee planned a diverse program, attractive for everyone in the community. Please have a good look at the website. Registered participants can attend the conference via Zoom, but also YouTube and Slack channels have been set up. And by the way, please mute yourself if you're not speaking, and the meeting is being recorded. Finally, I hope that our oldest member, Kees de Jager, whose 100th birthday we just celebrated, is watching. I thank the SOC and the LOC members for their efficient preparation of this conference, and I encourage you all to look at the posters. I now hand over to Sven de Rijke in Ghent, this afternoon's chair, wishing us all a great conference. Thank you.
Thank you, Peter. And without further ado, I would like to give the floor, or at least the virtual floor, to Monika Moskibrodska of the Radboud University, who will talk about the imaging of magnetic fields at the edge of M87's black hole.
All right, thank you very much. It's really a great honor and pleasure to open this conference with my talk. Thank you very much to the organizer for inviting me to give this presentation. So I will be speaking on behalf of the Event Horizon Telescope collaboration about this very brand new exciting discovery of polarization of the ring around the shadow of the black hole in M87 galaxy. And the image that you see on this front slide here is a result of a couple of years of work, data calibration, data analysis, building models. And this is, by no means one human job. There is plenty of people standing behind it. I'm representing them here. As someone said recently, it takes a village to image a black hole. So many people have been involved in this data processing and imaging and interpretation. Not all of them are shown in this picture here. But let's start from the beginning. Some basic information. What is the Event Horizon Telescope? It's a VLBI experiment operating at high frequencies at short wavelengths, 1.3 millimeter or 230 gigahertz. This is how the array looked like back in 2017 in April. Now it's growing, it's bigger, we have more stations. This is the configuration from 4 years ago. In April 2017, we collected the first data set that allowed us to make a first image of the black hole shadow in the core of M87 galaxy. This was published more than 2 years ago now, and attracted a lot of media attention. This was, of course, not the first millimeter VLBI observations ever made, but the number of stations that joined back in 2017 allowed us to collect enough data, enough spatial information about the source to construct this kind of maps. What are the basic properties of this image? Its diameter is about 42 micro arc seconds. This corresponds to 2.5 Schwarzschild radius. And this is, what's expected to be seen around the black hole shadow. The ring is almost perfectly circular, and it has this asymmetry which makes it brighter on the south side. This kind of asymmetries are easily explained as such by effects such as a relativistic beaming, a relativistic Doppler effect. So something probably is moving in the source almost at the speed of light. And the third thing to say about this ring, that the ring itself has a very high brightness temperature. This means that at this wavelength, it's most certainly produced by relativistically hot plasma producing synchrotron emission. So what we see at this wavelength is synchrotron emission. And as you know, synchrotron emission, it's a non-thermal process, so it's polarized, and it can be up to 100% linearly polarized at the emission location. Depending, the exact level of polarization really depends on the plasma conditions. So what can we actually learn from polarization? What the polarization can help us to understand about this ring? Almost everything. So since the publication 2 years ago, we were looking at this ring and wondering whether this, the ring emission that we see is matter flowing towards the horizon, maybe on the beginning of the jet, or maybe just swirling around the object. Is the black hole spinning, or is this image going to change in the future, or is it going to be the same in the future or similar? And the final question is, how is this ring connected to a kiloparsec scale jet that we do see in M87 galaxy? So this is like the main basic question. And we know that this jet is probably driven by magnetic fields, a magnetic process from the black hole. So, measuring polarization can tell us something about magnetic fields around the black hole, and maybe can give us another clue, not only about the nature of this emission, but also, can help us to understand how the jet is launched. So before going into how we made the image and what it means, I just want to explain what are you actually looking at. So I'm going to start with these two plots that basically show the same thing, that show polarization of the ring. So in our two publications that were released in March earlier this year, we show polarization using these two types of visualizations. So the left one is similar to what is usually done in standard VLBI business. This plot shows polarization on the top of the total intensity. So total intensity here is shown in a grayscale. On the left, this is something that you have seen before, all in orange. And now it's gray, and total intensity is put in a background. And on the top of that, we plot polarization in forms of the ticks. These are the polarization ticks. This is a linear polarization. Basically, the tick orientation tells you in which direction the electric field vector of electromagnetic wave that we see at our instrument, in which electric field is oscillating, and the tick length is proportional to polarization flux. And the color of the tick encodes the fractional linear polarization. So you can see that the ring is weakly polarized, up to 15% at most, okay? And the rest of the ring is depolarized. And the polarization is mostly in the south and the east. South and west, and it's depolarized in north and east. And we usually put small number of ticks on the top of such image. That's because polarization data is the same VLBI data as the one used to construct intensity maps. It doesn't have higher resolution at all. So we usually put few ticks per beam size, which is here 20 microarc second. That's the resolution of the EHT. And the right picture on the right, the orange one, depicts the same polarization using so-called line integral convolution in which we have total intensity is shown in orange, and this brush stroke that you see on the top follows basically the EVPA vector field. And this type of image representation is used as an outreach. Many other collaborations use this type of visualizations. For example, Planck collaboration, or recently also Gaia collaboration shows that to show vector fields or motion of things. This image may give you an impression that we have that polarization sees something more clearly, that the resolution is higher, but this is not the case. Our resolution of polarization is exactly the same as total intensity. It's just 20 microarc second, nothing more. So you have to keep that in mind. But the most important thing is that what you see here on this left panel, it's not a magnetic field yet. This is just electric vector position angle. So that shows the direction in which the electromagnetic wave is oscillating. All right, how these images were done. So the data used to create this new version of M87 image is the data that we have collected back in 2017. So it's exactly the same data that were used to make the first ever images of a black hole shadow. In April 2017, we have observed M87 for 4 days within 1 week. This is how M87 polarization looks like in a UV space, in a Fourier domain, in other words, because EHT is an interferometer. This is what EHT sees. Color codes here, fractional polarization here, but it's an interferometric polarization. This one can be actually higher than 100%. That's normal. It is evident from this plot that M87 is weakly polarized source, but it also shows small variations from day to day in polarization. And M87 is also a compact source, so it's a perfect calibrator for polarization. So it became its own calibrator. So how to make images from that? Well, in VLBI process, to make images, one has to have a very good understanding of our heterogeneous array and all its elements, and observing conditions that may introduce errors to our measurements. And in particular, when we talk about polarimetric imaging, just like in standard VLBI polarization, there is a polarization leakage. It's a property for each antenna in an array that can make unpolarized source look like polarized one. So these leakage terms are usually of the same order as the source polarization. So this imperfection of antenna receiver have to be estimated from the data in sort of like an iteration way during the imaging process. And this is actually one of the hardest part in this whole process. And the first attempts to make polarization image of M87 came very early, almost simultaneously during when we were publishing total intensity maps. Here you have some preliminary results from 3 very well vetted sources. EHT imaging is developed, it's a regularized maximum likelihood method developed by Andrew Shale and his collaborators. Pulsov and LPCAL. Pulsov is based on CASA, and LPCAL is probably a tool that many of you know. In radio astronomy, the most used software is APES. So this is a tool in APES that together with DiffMap, you can make this kind of polarization images. So, first of all, we have not used any special techniques here. Some of these techniques are very well known to the community. We were able to already make this kind of maps 2 years ago. And already these preliminary maps look very similar to what we have presented finally recently in our press release. And the leakage terms for each antenna also look similar, although they have small spread. And the next step in EHT process, in imaging process, is testing all these algorithms. So since each method of imaging has its own free parameters, we have to find out, what are the best values for those free parameters. And in algorithm testing, usually we create a synthetic data based on some model images. We try to make these mock images as diverse as possible, as you can see on this slide. And we then convert this type of images into synthetic VLBI data, corrupt this synthetic data by instrumental noises that we know of. And then using this mock data, we try to recover the truth images. So this is a typical way of doing not only polarization maps, but also total intensity maps. And here is an example how different imaging methods can recover this kind of synthetic simple image. In the bottom, you can see 5 reconstructions of the top right model. And because polarization is in general more difficult in this case than the total intensity, it has this additional instrumental noises, the leakage. We have eventually implemented 5 methods to make polarimetric maps. So for total intensity, we had 3 methods. Now we are paranoid, we have 5 methods, 5 very distinct methods. I don't want to go into details of each of this method. What I will show you just how do they work on the real data. This is how individual methods will produce, what kind of images they will produce using the real M87 data. This is April 11 data from the last day of the observations. So, there are some small differences between these maps, which are due to peculiarities of this each algorithm. But, all images shows remarkable similarity. And more or less they saw what we saw initially. Okay, ring is partially polarized southwest up to 15%. What we have shown at the end in our press release is actually method averaged image. So we stuck them all together. And here you have those method average images for each day of the observation plotted in 2 different ways. And if you look at just at this top panel, you can immediately see that these images show that M87 polarization actually is changing from the beginning of the week to the end of the week. And this is consistent with what we have observed initially in the source in total intensity. There is some kind of evolution in the source that is happening in the source. It's that doesn't seem like it has anything to do with some error that we make. All right, so now the very critical step in polarization of M87 was to actually go back to this calibration and to, these are the calibration terms, the leakage terms per each antenna determined together during the polarimetric imaging process. It's an iteration process, as I said. So we have to understand, you don't have to understand what these points really are. You can see more or less that they are consistent with one another, but there is some small spread, and this leakage is not really a variable. It's a fixed number per antenna. So we had to check how our fiducial images change within this spread of calibration. Okay. And you can see that these quantities here are given in percentages. So this leakage polarimetric, this is the instrumental polarization, is of the same order as the source polarization. So we really have to have a good handle on this. So this was another very long exercise. Actually, this was done via Monte Carlo simulation. This is really took a lot of time, because for each method we have produced 1,000 fiducial polarimetric maps, with each of them with leakage slightly off. Okay, so here on the left you can see the distributions for medians and standard deviations for this leakage that goes into Monte Carlo simulation. And the movie on the right shows you how stable the polarimetric images is against the leakage calibration. This is just using example of one pipeline and one day. And the movie shows you a series of these 1,000 images. The conclusion here is that if we have made some small calibration errors, then this doesn't really affect the image. The image is robust. Okay, we see the same level of polarization in all of these maps, and polarization location inner ring is the same, and it shows this nice azimutally oriented ticks. And we have repeated this exercise for all methods and for all days. So the results look very similar to this one. So, you know, finally, it's not like each does not produce one image made by one person, okay? We have 20,000 of them, 1,000 per 5 methods for 4 days, okay? So, you know, we choose at the end some one that represents this observation well, but you have to keep in mind that, you know, there's many images there. And to quantify, how to quantify these images, this is, you know, how to describe them, because that's important. This is what we want to do at the end. We want to compare the observations with some model and actually learn something about the source. So this is important question. So we have actually used 4 polarization metrics that are shown here on the slides. So the simple one is the image net fractional polarization. There's also a mean image polarization that is basically measures the more or less the order of polarization in the image. And the last one introduced by Daniel Palumbo is called beta 2 function. It's a sort of, he came up with a decomposition of complex polarization into this azimuthal modes, and it's been found that M2 mode is actually best in this function to discriminate models, okay? This beta function is actually a complex number. It has amplitude and phase, but you know, this is just a number that characterizes the image polarization. And on the plot here, you can see a few synthetic polarimetric maps. These are models of M87 based on MHD simulations to show you, you know, how these numbers different, how are they different for this kind of different maps. So what we have done with observations, we have actually computed distributions of these 4 metrics using our samples of 1,000 images per method with slightly different polarimetric calibration. This is how this distribution look like. They don't always look like a Gaussian, but you can estimate the mean and some standard deviations. So we do that for each method separately and for each method separately. So now I want to move on to the second part of this talk, and I think I have to speed up really. You know, how to compare the observations to models, yeah? So the polarization of light, the direction in which these electric vector oscillate is locally perpendicular to magnetic field, but near black holes, everything gets distorted by gravity and other effects. So what distant observer sees can be different. So we cannot just, you know, rotate this ticks by 90 degrees and say that's magnetic field. That's not the case here. So we will want M87 model to recover our 4 metrics of the image produced by EHT, which is not a single number now because of this calibration errors and imaging methods errors. But it's rather a range that encapsulates, you know, all the uncertainties in imaging methods and calibration errors. And EHT measured linear polarization, but, you know, synchrotron emission can be also circularly polarized. So we also put some constraint on circular polarization and use that as an additional constraint on the models. And how we have interpreted this observation, well, M87 is a low luminosity AGN. It's probably surrounded by some advection dominated accretion flow, geometrically thick, optically thin, hot accretion disk. This does not emit much of the radiation. It does not cool rapidly. It probably launches also a jet. And we have used numerical models of such accretion flow. This is all based on general relativistic magnetohydrodynamic simulation. So we have a library of GRMHD simulations in our collaboration. This is the same library that has been used to model or understand M87 ring 2 years ago. This is a polarized version of it, or rather a sample of polarized snapshots from the whole library. Here on the top of the total intensity, which is shown in orange, you see ticks that represent the model polarization. And what's in this library? Well, we consider 2 types of models, SANES and MADS. SANES, the disk insane, which stands for standard and normal evolution. The disk is turbulent. MADS are more magnetized. These are the magnetically arrested disks. MADS have also more powerful jets. And we pick 2 snapshots from each simulations. We compute them for 3 similar inclination angles, and we also assume that, or let this advection dominated accretion flow to be 2 temperature in the models, because ADAFs could be 2 temperatures. And finally, we consider models onto accretion disk, onto non-spinning and spinning black holes. And we also take into account cases in which the whole accretion flow can be spinning in the opposite direction than the black hole itself. At the end, we have 72,000 model snapshots to compare to. All these models, of course, are generated using some, radiative transfer models. This is all based on general relativity, relativistic polarized ray tracing methods. I'm going to skip the details here just to give you a quick sense of how different magnetic field configuration around black holes may look like. Here is an example that shows how EVPA's patterns produced by pure modes of magnetic fields will look like. These simple examples are quite instructive to get like a sense of how magnetic fields configuration look like in a strong gravity, but simple models do not include 3 things. That's why we don't really want to use them for interpretation. So first thing that is missing here is that in reality, magnetic field is not the pure mode, probably. It's a combination of the 3 things. The second thing that these simple models do not include, but our GRMHD simulations do include, is the effects of Faraday rotation. So we found out that GRMHD model polarization patterns can be also distorted by internal Faraday effects, such as Faraday rotation that happens in a source at the same location as the emission. And this Faraday rotation internal can non-uniformly rotate the whole map and even scramble it up. Then such scrambled map, when blurred to the nominal resolution of EHT, which is 20 microarc second, will be depolarized. This is consistent with what we see in M87. So our current idea is that this ring depolarization mostly comes from some kind of internal Faraday rotation that is happening in emission zone. So that's one thing, one effect that is included in our models. And the second effect that is included in the models, but not in semi-analytic models, is the fact that MHD models are variable. So we can in some sort of sense include the variability. All right, so what we do, we have now 72,000 snapshots like that. And we calculate image metrics for all of them. This is how the image library looks like in terms of metrics. We have divided here these histograms into SAINs and MADs on prograde and retrograde orbits, and ranges allowed by EHT polarimetric images are marked with these vertical shaded regions. How do we decide which model is consistent with M87 observations? Well, we came up with 2 scoring methods, but I will have time only for one. One can basically do the simultaneous scoring. So we rule out models where none of 600 snapshots in a given model can simultaneously satisfy all 5 observational constraints. And this plot basically shows you the number of passing images per model type. This is marginalized over some electron-ion coupling ratios. But it turns out that only a very small fraction of images that we have in our library satisfy this observational constraint. Actually, only 73 snapshots out of 72,000 snapshots is consistent with the observations. All of these models, but only 2, are MADs, magnetically arrested disks. And most models with more than 5 passing frames are MADs that are accreting onto either non-spinning black hole or a black hole with a small negative spin, which is kind of surprising. But so in general, MADs are favored. But here I'm showing you a few examples of models that are passing and failing this simultaneous scoring. So the top one is passing, the bottom one are examples of maps that are failing. They are either too overpolarized or too depolarized or too organized. All right, so let me summarize this whole new thing. So what are the new lessons learned? For the first time, we have constrained geometry of magnetic fields and measure the polarization on such a small scale, so close to the black hole. This has never been done before, so it's a new lesson on its own. And this movie here, this animation shows you one possible scenario of how magnetic field structure may look like close to the event horizon. It's more like a twisted tornado, but keep in mind that it's very difficult to visualize magnetic field geometry in a space-time that is curved and twisted by rotation of the black hole itself. So it's just some kind of projection onto Cartesian space. And we have also other models with slightly different configuration of magnetic fields that could also explain. So this is just one of the examples. And the second thing that we have learned is that we have now a slightly better constraint on how much matter is falling onto this black hole. In solar masses per year, it's actually now narrowed down to about 10 to the minus 3 solar masses per year. This is also much smaller than mass accretion rate estimated from X-ray observations in M87. From Chandra, at the Bondi radius, it's 0.1 solar masses per year. So if there's some accretion flow there from Bondi radius towards M87, there's also massive outflow. There must be massive outflow from this system. And finally, as it comes to the jet power, this is another thing that we would like to estimate close to the black hole. The new estimates, the new observation do not really better constrain the jet power. Because our jet power in our models does depend on the black hole spin, and we find models with this different spins to be consistent with this new observation. So at this point, there's no spin estimate for M87 black hole. That's because polarization is really not sensitive to spin, in generally speaking. It's more sensitive to this to temperature structure of ADAF. And this jet power at the jet launching point is of the order of between 10 to the 42 to 10 to 43 ergs per second. So this is, for example, much lower than what has been estimated at scales of 80 kiloparsecs from, for example, LOFAR data. So LOFAR estimates for the jet power in M87 is something like order of magnitude larger than that. And we don't know how to describe this discrepancy right now. How to explain this discrepancy right now. Okay, so here are my summary slides. EHT collaboration has just published near horizon information for the second time. These are the first ever polarimetric images on these scales, and polarimetric images put much stronger constraints on any theories which will try to explain this ring emission or jet launching theories. And of course, here I will not read this text in a smaller font. You can read it yourself. The conclusion here, the main conclusion is here that these models don't include everything, all the physics that we would like to include. They probably could be still improved, but we can still explain what we see in EHT using the physics that we know of. There's nothing really unusual here. We can still, we still have models that can explain the observations. And future observation in EHT will be done in much wider frequency band. This will allow us also to complement this kind of polarimetric maps with rotation measure maps. There'll be more information. There is some chance maybe to even do circularly polarized maps. We will study in the future also variability, and ultimately EHT polarimetry should be done in combination with multi-wavelength observation. So there has been also a publication about that just last month ago. This will be super constraining for all models. And of course, the second target of EHT, Sagittarius A*, we can also do polarimetry there, but we're still waiting for total intensity images for that source. So I will skip this topic. At the end, I just would like to say that, explaining M87 jet may have also a broader impact. Of course, this is, as you know very well, this is not the only jetted sources that we see in the universe. And hopefully we made now just another small step that hopefully will add significantly to some big leap for the entire field of high energy astrophysics. I think that's all I wanted to say today. Thank you.
Thank you very much. I see one raised hand for a question.
Should I read it myself or are you going to talk to me?
Yes, so please, I don't know your full name, Harish, you can ask a question.
Oh, thanks. Yeah, Monica, my question is, do we know the Lorentz factor of the electrons that are emitting? Is it like somewhat a thermal population at 10 to the 9 or 10 to the 10 Kelvin, or is it a small number of electrons which are like a power law and much higher Lorentz factors?
We don't have yet constraint on what exactly is the particle distribution function, the electron distribution function. In our models right now, we only assume that it is thermal, Maxwellian thermal, but relativistic, and we have some constraint on temperatures. And
But
those
wouldn't
temperatures
that
would
have
be
a...
of the order of like between 10 to the 10 and 10 to the 11 kelvins. So I don't know how to translate that into KeVs. It's a hot plasma.
Hot, yeah. I guess I asked that because you said that some of the depolarization is not because of intrinsic geometry of the magnetic field at the emitter side, but it's because of differential Faraday rotation. But this assumption matters for the Faraday rotation, right? Because most of the Faraday rotation comes from 10 to the 9 Kelvin plasma. And how much of it exists there?
Yeah, I think this is an excellent question, but I don't have an answer. It's just when the parameter space for particle acceleration, you know, especially when you talk about GRMHD simulation, is kind of large because this distribution may be changing, you know, in space around the black hole and also in time, may depend on the certain conditions or some events, reconnection events that happen in the simulation. So we don't really have yet a good handle how to model this properly in MHD simulations. Hopefully this will change in the near future. Yeah, I think that, yeah, assumption of, right now we just assume thermal, relativistic, but thermal plasma.
Okay.
The parameter space of this non-thermal business is too large yet for us to, you know, fully explore and draw any conclusions. So we rather not comment on this yet.
Sure.
But it's a very relevant question, very good question.
Okay, thank you. We have time for one more question. I have one short question, actually. The accretion rate, how does it compare with the Eddington rate?
What's the Eddington rate in this?
So how much can it be accreting compared with its luminosity?
Yeah. I think so. I'm trying to recall. Okay, it's 10 to the minus 5 in Eddington units.
Okay.
It's 10 to the minus 5 Eddington mass accretion rate. So it's slow in terms of Eddingtons.
Okay, thank you. If there are no further questions, I would like to thank our first speaker of the day. I don't know if you can give virtual hand claps. And then we move on to Ronnie Kappens from Leuven University in Belgium.
So I think I'm sharing my screen now.
You are.
And this should be full screen mode. So I hope all is visible for you. So I'm very glad. Okay, thanks. I'm very happy to be here and to be able to give you a little bit progress on solar flare modeling. So this is work done that is also part of my ongoing ERC effort. I termed it When Hot Meets Cold, and hopefully by the end of this talk, you will agree on what I meant there. So let me give a brief introduction. Solar flares are essentially the biggest bombs in our heliosphere. As astrophysicists, we are very much interested in explosive phenomena. And so if you restrict your attention to the heliosphere, then solar flares is your cup of tea. This is a picture of our sun, actually dating back from May 2013. There is some composite images. Essentially, we're seeing the sun light up in extreme ultraviolet. So we have, in contrast to the previous speaker, we have the advantage of having everything nicely resolved, and further resolution is coming with new missions. You can see here that the sun's atmosphere is filled with coronal loops, these structures that are nicely seen here in these UV images. And then occasionally something explodes, and that's the solar flare site. This particular was a so-called X-class flare in May 2013. So the flare alphabet really goes like ABC and then MX, in the sense that the strength of a flare And a flare, it can reach enormous strengths. I mean, you can you know, compare it to 1 trillion times the little bomb, the little boy that was dropped on Hiroshima. But of course, they don't all reach the same levels. And here we have a particular event. So this is actually a few days in around July 2000, where we actually have light curves, essentially the X-ray flux as measured by this GOES satellite. And that's essentially what then, you know, classifies the flare. And so, for instance, here in this red channel between 1 and 8 angstrom, you see here there are these enormous peaks. This one is a peak particularly favored by the French because it occurred on July 14, 2000. So this is the Bastille Day event. It's an X6 class. So it's really like on this kind of logarithmic scale, you read off where you actually reach the level. And just to give you a little bit of flavor, like in September 2017 was the most recent strong event, and strong in this scale of X 9.3. The strongest, basically in the years 2000, in this century, was actually the so-called Halloween storms event in 2003. That actually reached X28 plus, and now they're even talking about recalibration because everything's saturated, so it should be X45. This was leading to like a 1-hour power outages in Sweden. So these things really do have effect. They also cause trouble for various satellites. So you can imagine that solar flares, and especially, of course, the strongest one, are very relevant for our modern day society, where we rely on so many satellites and GPS and you name it. In fact, if you like classifies, then here there's a website. You can check the top 50 solar flares of the year 2021. So we are a bit lucky because, well, so far in 2021, we reached up to this M class. The point is that, as you probably know, the sun's activity, which is magnetically driven, basically, and manifests itself as sunspots that appear on the surface and then disappear again. Basically, it waxes and wanes with an 11-year cycle, and this cycle 25 started late 2019. So if you want to go for a lot of activity, just wait a few years, 2023, 2024, we'll definitely get some more X-class flares. What is actually happening in a flare is, well, typically collected in cartoons. So this is an early cartoon from 1989 by Piet Martens, where the black lines are actually indicating the field lines. On the right, you see basically an equivalent magneto-hydrodynamic simulation, so not general relativistic as the previous speaker, but just Newtonian MHD suffices here. But we have magnetic field lines. They basically, when you have a flare, then what we know is that magnetic field lines of opposite polarity come together in a current sheet. That's where all the magnetic energy gets converted to other forms of energies, both thermal, but also accelerating non-thermal particles. So electrons, they go down the magnetic field lines, they are guided, then they basically interact collisionally with the denser lower layers of the atmosphere, so-called chromosphere, and below. And this is essentially the picture, and every aspect that we have observationally established is sort of mentioned in this picture. And so on the top, of course, we have the erupting flux robe with potentially a prominence in there. What I'm going to focus on today is basically the bottom part. So what's happening here in this so-called flare loop system. So what happened since cartoons is that cartoons have become prettier. So here, this is the 2017 one from sort of an overview paper there. Again, so the cartoon collects all the information. We know that there is magnetic reconnection. We know that there is non-thermal electron beams that basically travel downwards. They interact here. They cause the so-called flare libands. So there's the foot points that actually separate. And of course, there is a 3D structure here. Energies, as I said, enormous, can be enormous. Up to 10 to the 32 ergs can be released in minutes. There is magnetic reconnection. There is hot, several tens of million Kelvin plasmas. And there are these non-thermal electron beams. And the hot plasma and the non-thermal electron beams and the magnetic fields, etc., are dynamically feedbacking on themselves. Now, this cartoon has been around for a long time. Again, it just became prettier, but state of the art is that typically, if we model solar flares, we either do a pure magnetohydrodynamic simulation, where we actually don't have any non-thermal plasma, or we take account of the non-thermal electron beams, but then we typically do that in 1D model. And then when I say we, that I mean the solar physics community. In 1D prescriptions along magnetic fields, you actually then can take fairly advanced non-thermal beam prescriptions. Or you can do a local particle in cell treatment, which is of course completely self-consistent, having all the accelerated particles and the magnetic fields, Maxwell's laws taken into account, but typically on scales that are much too small to be talking about this whole low flare system. Or one can do global simulations on the one hand with MHD and then look at the fate of test particles. Or, and that has also been demonstrated, take a global MHD and then use that somehow as a background and as a boundary condition for a global PIC treatment. But note the missing back arrow. So that's the state of the art today. That is Geran, my PhD student, and Chunsha and myself, we have last year published a fully self-consistent model for solar flares. And I'd like to explain to you in which way we are here self-consistent. What we are actually doing is we are doing magnetohydrodynamics, and we address the role of these non-thermal particle beams in the MHD evolution. And so just because I like them so much, I show you the MHD equations, conservation of mass. This is the momentum equation. So we have gravity, obviously, we have the Lorentz force. And then here in the energy equation, I'd like to point your attention to the fact that, okay, we have to do, there is work by gravity. There's, of course, the Lorentz force also here. There is anisotropic thermal conduction, again, in the strongly magnetized low beta coronal plasma. Thermal conduction happens mainly only along magnetic field lines. There is an anomalous resistivity that we will use to just sort of initiate and follow the reconnection. And then there are all these terms here. And the ones that I circled here are the ones that are new with respect to previous works, which are energy losses due to fast electron beams, and then heating resulting from fast electron beams. And I'm going to explain to you briefly how these are actually taken into account. So as I said, there is this resistivity. Resistivity normally, just if you were to do regular resistive MHD, you would indeed convert magnetic energy to thermal energy and kinetic energy. But now what we do with this term here in the fast electron beams, we actually take a fraction of the local ohmic heating, and we basically extract it from the MHD system. In fact, we do that only in sites where we have the downward reconnection and where we have hot plasma, and everywhere else we don't get that. So the part of the Joule heating will be used for non-thermal beams. And what do we do with that? Well, we let it dynamically feed back in the MHD at a different location at a different time. And how does that happen? Well, this here is supposed to represent a snapshot of things where, okay, so the colors, they are just indicating that, of course, we have a dynamic adaptive grid with different levels of refinement, and they are distributed over different processors and the colors. So we do what normal modern computers can handle. But then we have a magnetic field that also changes. So here is just the instantaneous topology of the magnetic field with these black field lines. In this side here, the beams get energized. Then we have a prescription for field line guided energy transport by beams. The beams, basically, they are aware of the column densities that they encounter, and so they collisionally interact, especially with the dense chromosphere. They can also here in this site, for instance, notice that the magnetic topology here might actually be beneficial for mirror traveling. And so that means that energy that is taken from the plasma here might be deposited somewhere here later on. And that means, technically speaking, we have to interpolate back and forth between changing grid lines and changing AMR grids all the time during our simulation. And that's, of course, what makes it technically challenging. Now, what does it look like? I'm going to show you an evolution in density, temperature, and the vertical velocity component that basically will just show you how the initial reconnect. So the initial magnetic field that is not shown here was just a current sheet in the middle. This reconnects here, and then you form here the post-flare, well, the flare loop system here at the bottom. And so I'm going to play this once more and point you to the fact that there is this black region here. Okay, I just played it backwards. So the black region here is where the energy locally gets extracted. And what you see here is that's where the energy gets dumped. Okay, that's this non-local energy transport that we have. So we do have a realistic stratification. So we have a chromosphere transition region corona classification. And in this process, if you looked at the temperature, we start with a 1 million degree corona, but in this flaring process, we reach several tens of millions, really hot. We can take these NHD simulations and turn them into synthetic images, both the soft X-ray, this is the thermal emission, this is at about 10 keV. And then also, because we have this analytic prescription for these electron beams traveling along field lines, we can actually quantify hard X-ray. And so here, this is basically showing you two simulations at the same time. So where you will have in reddish the soft X-ray, and in the black contours, you have the hard X-ray. And so what you notice is that in the left, you have just two foot point sources, and in the right, you could see that there was also a hard X-ray loop top source. The basic difference between the left and the right picture was that this analytic beam model has an ability to basically, well, follow the pitch angle and also quantify the pitch angle, so the average pitch angle of the injected beams, and then this basically initial pitch angle may become aware of the locally changing and the locally forming magnetic mirror, and that's indeed the explanation of why this case forms a loop top source and why this case does not have a hard X-ray loop top source. In these simulations, you noticed that there were these foot points that, as a function of time, were basically separating. So this is the left foot point, this is the right foot point. We can actually quantify this. They separate with about 125 kilometers per second. And what is shown here at the right is then a measure that you can actually get observationally. Indeed, you can see with in the observations the separation of these foot points. You can also quantify the foot point magnetic field, and this is here compared to what the simulations can, but the observations cannot quantify, namely the reconnection rate at the X point. And you can see that they match very well. And this is sort of expressed here in this VB equality between foot points and what's happening at the reconnection site. And so that is a powerful tool to quantify the unknown reconnection rates. Now, I promised you in my title that I'm going to tell you also about something cold. So far, I've only talked about things that started hot, 1 million degree, and got hotter, a few tens or up to 40 million Kelvin. When hot meets cold, that is something that we are now looking at with continued simulation of these flares. So far, I've actually concentrated on this impulsive phase. This impulsive phase, you have magnetic reconnection, you have the generation of these non-thermal electron beams. Main energy release that happens essentially within a few seconds up to minutes, and then the main bulk, of course, within tens of minutes. But there is a gradual phase to all flares that can last hours, and in the soft X-ray there is this gradual decrease. So what happens in this gradual cooling phase? Well, we do numerical simulations, and we have computer power nowadays. So why don't we just continue the simulation for a while? And if we then continue the simulation, again here, what I'm going to show you also in a movie is something that, again, will follow this course here. Here, we indicated that this was this current sheet, so anti-parallel magnetic field line started off. You have then the formation of this current sheet, the flare loop, of which I talked about. And so in the soft X-ray flux at the bottom here, you have this impulsive and then this gradual phase. And now we just continue this. And so if we continue this, and now I'm just going to show you the density evolution. You see here what's happening. So dark, I should say, is of course dark. So there it was. You have dark, so very dense material that forms spontaneously in the post-flare loops. So I'm going to play that once more because I like it a lot. You see here again, you have this post-flare evolution, and all of a sudden you form these condensations. So the contrast in density here is, again, this is essentially low temperature, so low means here 10,000 Kelvin or so. And again, a contrast of about a factor of 100 in density. And you saw that there were two cycles in the movie that I played. This is the blue curve actually shows this coronal matter, this cool matter that formed into the corona and then slided down, rained down again. This is indeed called coronal rain. They are coronal rain cycles that we actually found now in this post-flare evolution of flare loop. In fact, you can also then look at what does this rain, which is here now shown in these kind of blue contours, that's where the cool material is at these particular moments in time, is actually then causing effects on its surroundings, because of course the thermodynamic properties of the surrounding plasma get influenced. You see here how in an extreme, in an EUV view, you actually originally here had a hot loop. Okay, here you had a hot loop. Then this is 51 minutes. This whole hot loop suddenly fades. This fades for another, well, 10 minutes or so. You see 58 minutes, there is still no, and then it brights up again. So in this coronal flux in EUV channels, these rain-induced temperature changes make nearby loops disappear from EUV channels. So again, this is when hot meets cold. There's a lot of interesting thermodynamic changes that happen in these things. So with that, I actually have given you pretty much all of what I wanted to talk about. I'm just going to give you a little bit of an outlook and a summary. So the takeaway from what I talked about today is that if you're interested in solar flares, and maybe you're not interested in solar flares, but maybe you're interested in explosive phenomena somewhere else in our universe, then actually you should be interested in solar flares, because those are the ones that we can study observationally close on, and we have the best models now available so far. There has to be feedback between the thermal plasma and the non-thermal plasma. It's essential in any flare, not only solar flares. And this is the picture that we had, where we had, for this case, where we had these foot point hard X-ray sources. These things we can quantify, the velocity and the magnetic field at the foot points, and they tell us what's happening at the unknown reconnection site. There are extreme density and temperature regimes throughout all flare phases, also this long duration post-flare loop, third post-flare flare. And what we are going to do next is, well, these simulations were done in so-called 2.5D. So I showed you everything in a plane, but there were also magnetic and velocity components out of the plane. We can generalize that to 3D. We can look at the fate of the flux rope and its eruption. We can basically, I started with telling you about the flare alphabet. The flares that I just discussed were meager flares, like B class. We can do this now across the flares classification scheme. We just have to sort of upscale the magnetic field strength. These were about 35 Gauss or so magnetic field strengths that we took. We can look at stronger field regimes and then see what's happening there. We can look at the role of asymmetry. There's a picture here where you see we have also looked at cases where there is not a nice left-right asymmetry. We, of course, if we look at the reconnection details in these current sheets, we have these plasmoids. The same plasmoids are crucial for flaring effects in accretion disks around black holes. So again, we share a lot of interest here. Another thing that we share is the infrastructure and code. This is basically all done with an open source code. I invite you to look at that, amrvac.org. Everything you want, you can reproduce. And with that, I'm going to stop, and I'm going to just let this thing here play during the time that you may have questions, just to show you what a flare looks like in reality, this May flare from 2013. And so it will happen here. And later on, you will see both effects that I talked about, so the flaring, but also the coronal ring. So thank you for your attention.
Thank you, Ronnie, for this wonderful talk. Questions? I see there are questions. Please, Harish.
Yeah, I had a question about how the relativistic electron, so the electron beam in your simulation is losing energy. Is it through upper hybrid instability or cyclotron instability that they lose energy? The ones which are in the trap, of course, not the ones which are lost from the trap.
So you were asking about the energy for the non-thermal beams?
Yeah, the non-thermal beams. Are you actually simulating? I'm a radio astronomer, so I'm asking whether.
Oh, okay.
Yeah. So are you simulating the emission of Langmuir waves at the upper hybrid frequency or the cyclotron instability? Is that simulated, or is
no, not to that effect? What we actually have, it's an actual. It's a sort of a sophisticated analytic model for handling basically how, if you inject a certain energetic power law of an electron distribution with a certain power law index at the top of a magnetic field line, how does that power law change as you encounter, lower density plasma? And so there is Bremsstrahlung effects is essentially behind all the emission. So since that is a 1D model, there is not so much plasma physics in there than there should be. Yeah.
Okay, so you don't have wave particle interactions. That's what you're saying. So there's no emission of Langmuir waves. There's
no.
Okay.
What we have is on the one hand MHD. It is coupled to what is, at least in solar physics, a fairly sophisticated analytic treatment of fast electron beams along magnetic field lines, and that dynamically couples back to the MHD. So what you're asking is, in that sense, not yet done.
Okay, thank you.
Monica?
Hi, I have a very naive question, maybe kind of silly, but it seems to me that you have handle on everything. And is there anything in the solar flares that is yet not explained by the models that you have?
I'm flattered by the way you asked the question, but yes, there is a lot still to be done. I mean, again, I think the most sophisticated, or in reality, what we would like is, let's say, a full self-consistent, kinetic description, right? Where, for instance, the topic that was just raised by the previous question is actually self-consistently incorporated by doing, let's say, a global particle in cell type model. I think that has not been done, and that will certainly be more self-consistent than what I did. Some of the topics that I mentioned here on my outlook are also still worth pursuing. Yeah, I mean, I'm quite happy that we got this far, but there are still a lot of questions. Don't worry.
Okay, thank you very much. All people who work on Galactic Center are highly interested in this topic, of course.
Thank you.
Because we see flares there and we don't know exactly what they are. So yeah, I was just wondering, can we take something from this solar physics?
Yes, absolutely we can.
More questions? No. Okay. For a moment, I was afraid that you were going to announce your retirement, saying like everything has been solved. I'm very happy you stay. Okay, thank you very much for your very nice talk. And then
even if everything is solved on the sun, we have a lot of radio observations of stars with LOFAR, which I'll be happy.
There's a lot of universe outside of the sun as well. That's right. True.
Yes, and a lot of explosions.
Okay, thank you. So we move on to Manuela Vacchi. Is Manuela here?
Yes. Can you hear me and see me?
Both of those, yes.
Great. And what about the laser pointer?
Yep.
Okay, good afternoon. And first of all, I would like to thank the organizers for giving me the opportunity to give this talk, in which I hope I will convince you of the fact that the Cherenkov Telescope Array, or in short CTA, is a unique observatory to explore the TeV sky. So we are a bit far away from the sun again. This talk is given on behalf of the CTA Consortium by myself and in collaboration also with my colleagues Jakob Vink, Sarah Markov, Christoph Weniger, Andrei Barishev, and Jan Aschensweber. In this talk, I will start with a brief overview on the topic of the Gamma-Ray Astronomy. I will present the upcoming Cherenkov Telescope Array and its main scientific goals, and then I will draw my conclusions. CTA will help addressing several scientific questions, which are top priorities within the Dutch and international scientific community of astroparticle physics. For example, what are the sites and mechanisms of high energy particle acceleration in the universe? In other terms, what is the origin of cosmic rays? What are the physical processes at place in neutron stars or black holes? And what is the nature of dark matter? This is, we know that we have observed the universe at different energies, at radio, infrared, optical, X-ray, and gamma ray. So in my talk, I'm going to focus on the detection of gamma rays of energies around the TeV, which means the energies that are comparable or even higher of those that can be produced on the ground with human-made accelerator such as the Large Hadron Collider. To understand the most extreme phenomena in the universe, we can use not only the electromagnetic radiation of multiple wavelengths, but also the high energy messengers that emerged in the recent years as a powerful technique. So to probe the most violent phenomena, we can also use the detection of cosmic rays, charged particles, whose path can be deviated by the magnetic fields that they encounter within or outside our galaxy. We can detect cosmic rays in space and on the ground with different detection techniques. However, because cosmic rays are deviated by magnetic fields, we cannot use cosmic rays to point back to their sources. However, we can use neutrinos. We can also use neutrinos, which are neutral and only weakly interacting, so their paths can point back to their sources and they can be detected on the ground, actually underground. We can also use the detection of the recent detection of gravitational waves to probe extreme astrophysical phenomena taking place in the universe, and of course gamma rays, which are neutral and point back to their sources, and we can detect them in space and also on the ground, which is the topic of this talk. Gamma-Ray Astronomy is a fairly recent detection technique. The first imaging atmospheric Cherenkov telescope was WIPO, taking data in the 80s and 90s in the United States. You can see a large segmented mirror with a diameter of 10 meters and a camera equipped with photomultiplier tubes, fast light sensors. And with this single telescope in 1989, the very first TeV observation of the Crab Nebula was achieved. Building on the successful experience of WIPO, several telescopes and observatories have been built in the following decades, such as the current generation detector HESS, High Energy Stereoscopic System, which is taking data in Namibia since 2004. We also can perform gamma-ray detection in space, and we have the successful history of the Fermi-LAT Large Area Telescope in space since 2008. So since 1989, with the very first TeV observation by WIPO, today we have more than 200 TeV sources detected, and the field is rapidly growing. And in the past few days, we actually have learned that we also have a PeV Gamma-Ray Astronomy with the recent result, with the recent observation from the LASO experiment. But going back to the TeV ground-based detection technique that is usually called imaging atmospheric Cherenkov telescopes, how can we detect gamma rays on the ground? Well, you know that once gamma rays enter the atmosphere, they interact with it and they generate an electromagnetic cascade of electrons, positrons, and other photons. And these particles can travel in the atmosphere with faster than the speed of light in the atmosphere and induce the emission of Cherenkov light, which can actually be is quite aligned with the shower axis and can reach the ground, covering a quite broad area that we call the light pool, even if there is no water involved. This light pool, depending on the primary energy, the energy of the primary gamma ray, has an area of the order of 0.1 square kilometers. And this is the area that we can instrument with these Cherenkov telescopes that, as I said, are constituted by segmented mirrors with a diameter of the order of tens of meters and a camera built of several photomultiplier tubes, which are fast light sensor able to sample this emission, which occurs over time scales of the nanosecond. The imaging atmospheric Cherenkov telescopes constitute a mature technique which is in use, as I said, since several decades. And this, as an example, is an image taken by the HESS telescope of one galactic supernova remnant. Now, the technique is mature and has provided incredible results, and it's important to mention that, for example, the HESS collaboration was awarded the Descartes Prize for the scientific breakthrough a few years ago. And how can we do better? CTA builds on the technique on the same technique as these detectors, but CTA will use the same technique, but more telescopes spread over two arrays in both hemispheres, and it will use different detector sizes to cover a broad energy range. So how can we make it even better? CTA, using almost 100 telescopes in two hemispheres of different sizes, will achieve 5 up to 10 higher sensitivity with respect to current generation detectors, 5 times better angular resolution. We are talking about arc-minute resolution, and 2.5 times larger field of view. So to give you an idea, when we talk about the HESS, 5 telescopes in Namibia, this is an illustration of the known gamma ray sources, and this is what can be achieved by CTA. How can we do this? As I said, we have 3 classes of telescopes. When we talk about the highest energies for which the shower is extremely wide, several kilometers wide, and the number of photons which reach the ground is quite abundant, we use small size telescopes, 4-meter mirror diameters. This will be located in the southern hemisphere only, which is devoted to the galactic science. In the medium-sized telescopes, which have 12 mirror diameters, we'll explore the intermediate range, the TeV. And for the low energy range, the GeV, we will employ large-sized telescopes with 23-meter mirror diameter, so that we can collect the faint signal of the showers at these energies. CTA will have 5 sites, and in this slide I show you the red dots indicate the array site, where the telescopes will be located. In the northern hemisphere, the telescopes will be located in La Palma, and in the southern hemisphere, the telescopes will be located in Paranal region next to ISO Observatory in Chile. Together with the arrays, we also have the CTA, or the observatory offices, and the Science Data Management Center. The status of the project is described in this slide, where you see that basically here we are at the end of the design phase, and we are about to begin the construction phase, which will last for about 5 years. And this construction phase will imply a significant performance improvement with respect to currently running facilities, and a significant increase of the discovery space and high impact science. After the 5 years, we will start the operation and enhancement phase, in which, on top of the existing observatory, we will go towards the full scope configuration. In this slide, I would like to provide you a description of the Dutch participation, which begins nearly at the beginning of the CTA endeavor in 2006, under the leadership of Jaco Vink and Sarah Markov at the University of Amsterdam, which had a pioneering role in the creation and setup of the multi-wavelength and the first multi-wavelength and multi-messenger group, and also took part in the studies for the galactic science. Then the collaboration was established in 2008, and in 2014, the CTA, the Dutch camera prototype efforts were led by David Berge, at the time at the University of Amsterdam, currently in Germany. And then in 2019, the Small Size Telescope was established. The Small Size Telescope Consortium was established with a Dutch participation. In the meantime, I joined the University of Groningen in 2018. And in this year, in a few weeks, we will start joining the efforts towards the construction of the Small Size Telescope cameras under the leadership of Jaco Vink from the University of Amsterdam. And in particular, we will play a role towards the integration, testing, assembly, calibration of the focal plane unit, in collaboration with also the NOVA submillimeter group led by Andrei Barishev. If you want to hear more, I invite you to check out the NVO website tomorrow. This is the Dutch CTA group that is spread in 2 universities, the University of Amsterdam with Jaco Vink, the PI, Sarah Markov and Christoph Weniger, and collaborators. They work on mainly on particle acceleration, dark matter searches, transient sources, and multi-wavelength and multi-messenger studies, and on machine learning applications. While in Groningen, we are more focusing on the dark matter searches, machine learning applications, and the instrumentation in collaboration with the NOVA group. Now I would like to discuss the main scientific goals of the project, and starting with the Galactic Plane Survey, which is extremely awaited result because CTA, given the excellent performance in terms of angular resolution and field of view, will be able to increase the number of TV sources in the galactic plane by about a factor of 5, providing a much deeper survey than any gamma ray experiment before. And this is extremely important, for example, in the frame of the understanding of the galactic center environment, in which we expect to observe an unresolved, so far unresolved millisecond pulsar population, which could be actually responsible of this galactic center emission that has been reported by the Fermi-LAT collaboration. And actually it's a very hotly debated topic in the scientific community. Within the discussion, in the understanding of the sources of galactic cosmic rays, we know that supernova remnants play a very important role. One very prominent source that is considered in a very good source, possible source of galactic cosmic rays, is this RX J173946, a young supernova remnant and one of the brightest sources ever discovered in TeV gamma rays. This is in this picture, I show you the Hess measurement. So once again, is the declination as a function of right ascension, and the color code indicate the excess counts. And what can do CTA? Here you can see the simulated signal for CTA in case the gamma ray emission is due to accelerated electrons, and on the right the expected image, the expected photon distribution in case accelerated protons are present in this source. The important point to keep in mind is that given the angular resolution, the extremely good angular resolution, the sensitivity, and all these characteristics, CTA will be able to perform not only good pointing, but also spectral and time variation studies, which are essential to constrain the emission spectra and understand whether or not there is the acceleration of cosmic ray particles is at play in this environment and in general in supernova remnants. This is a crowded slide, but it's very important that we discuss this in the particle acceleration in relativistic jets. You have seen a little bit of this image in the previous talk, but in this context, it's important to point out the fact that this is a radio image that you have seen before, and in red you have the resolution, the angular resolution of Hess, an order of magnitude of the resolution of current generation imaging atmospheric Cherenkov telescopes, which is of the order of 5 arc minutes. And here you can see the resolution, the expected resolution for CTA. So for CTA, with CTA for the first time, we will be able to distinguish the structure between the inner and outer jets, and we will be able to perform spectral and time-dependent studies of time variability study of this source in order to understand, to better constrain the gamma ray emission, which can then be related to the different scenarios for particle acceleration. And keep in mind, once again, that with current generation detectors, these regions are just not resolved. So we will be really able for the first time to understand the environments in which particle acceleration takes place so that it can generate gamma rays. This is a very important topic, and this needs the input from the multi-messenger and the multi-wavelength community, especially the Dutch multi-wavelength community, in which here I try to give an overview, and I apologize if I overlooked some contribution, but it's not just a matter of gamma ray emission. To have a global understanding of the phenomenon, we need to join the forces and combine informations obtained in all the electromagnetic spectrum from the radio to the gamma rays. A little bit more about time variability. CTA will be a revolution in the transient sources, in the high energy sky concerning transient sources. CTA will have a real-time analysis frame and with a latency of less than 30 seconds. So alerts will be emitted towards the community to allow for rapid follow-up observation. On the other side, giving 20-second slewing capabilities, CTA will be able to point very fast towards the region where the action takes place, focusing the transient emissions that are of interest. And this means that CTA will be able to detect transient sources for the first time in TeV gamma rays. The main target, well, there are so many, from gamma ray burst, sources of gravitational waves, high energy neutrinos, and also galactic transient, such as microquasars. It's also another very important point, how CTA performance compares to current generation. And here we have the differential flux sensitivity as a function of the observation time for selected energies, which are in the observable range for the Fermi satellite. And you can see that we have a factor 10,000 difference. So CTA is really 10,000 times better in this particular topic. Again, when talking about transient sources, the synergies with multi-wavelength and multi-messenger science are extremely important, as it's been demonstrated in the recent years. So not only electromagnetic, but also multi-messenger with common observation in high energy neutrinos and gravitational waves. And in this frame, we have the current detectors, which have performed the first ever gamma ray follow-up of gravitational wave events with the birth, the dawn of the multi-messenger astronomy in August 2017 with the beautiful GW170817 event that you see sketched here, and also the results published in 2018 of the high energy neutrino event detected by IceCube in time correlation with the flaring state of a blazar. And here I would like to show you projected performance of how the GW170817 looked like for the Hess telescope. This I took this image from my colleague Fabian Schussler, who led the observation of the region where the GW170817 was lying in Hess. Hess could not find a significant gamma ray emission from this direction. And what would that look like in CTA? Well, this is based on simulations, of course, but it would take only 2 pointings for CTA to cover the localization region provided by the LIGO and Virgo gravitational wave interferometers. The last science topic that I would like to present is a topic in which I'm always also invested, is the indirect dark matter searches. And we know weakly interacting massive particles, also known as WIMPs, were created in the early universe, and they are predicted in supersymmetric extensions of the standard model. if we believe that dark matter is made of WIMPs, we then expect that we should observe in the final state of their annihilation stable standard model particles like gamma rays and neutrinos, and also matter and antimatter particles that we could observe with cosmic ray detectors. But let's focus on gamma rays. So with gamma rays, we can point back to the sources, and in this case, to search for dark matter, we can point to regions of the sky in which we know that we have dark matter dominated regions such as the dwarf spheroidal galaxies, the Large Magellanic Cloud, the galactic halo, and the galactic center. So these are objects that we are going to observe with CTA in the upcoming years. And again, also in the search for dark matter, where we have a broad community at the Dutch level, at the University of Amsterdam and in Leiden, and I'm also involved, and sorry if I forget some contribution. It's important to include multi-wavelength and also multi-messenger informations. With this, I have reached my conclusions. CTA is the future project for ground-based gamma-ray astronomy with superior performance with respect to current generation observatories. And it's important to stress once again that the full exploitation of the CTA science case requires synergies at the multi-wavelength and the multi-messenger level. Thank you very much for your attention.
Thank you very much for your talk. Questions from our large audience. Nika. Oh, that's just a hand clap. Another hand. Yeah. Anyone? Everybody is ready for a break. Nope. If not, do I hand back control to one of the organizers to announce the break, or do I have the power to do that? Okay, so then there's a small break for 15 minutes until 4. Then we join this Zoom link again. Okay, see you all in 15 minutes, well rested and provided with coffee. Bye-bye.
Very weird that people don't want to say anything about when it's about astroparticle physics.
Renier, I'm sorry, I was reading a message. I didn't hear you.
No, I'm just saying, I'm complaining that people don't ask you any questions. I think they're just. I think the talk was quite good. So I mean, it was not that difficult to ask questions, but people then don't do it. I don't know why. Maybe it's because there are too many other people that are too many other unknown people that are also listening.
Well, the Slack channel, maybe we can encourage people, if you're interested in getting involved. I mean, CTA, the fact that we're now officially part of it means that people can join from the Dutch community and get access to the data. So, you know, these are not just astroparticle physics. I mean, this is, as Manuela said, 10 to the 4 times better than Fermi, which is, you know, GeV range, and this affects everybody. So, you know, please ask us if you want to get involved.
No, I mean, I thought I saw this nice picture of the M87 jet and so on. I mean, there is a lot of stuff to be done on that. And I guess maybe Sven, this is for the next one. If you don't have questions, go to the Slack channel and look what people say and just read a question. I think that is maybe in a way. Or in the chat. Okay.
The question and answers on the Slack are still dealing with the previous talk. I mean, previous.
Yeah, okay. Joe, are you keeping an eye on the Slack for in case there's a question that's relevant to the current talk?
I am. Yep.
Yeah, there's not too many. Okay.
But the good thing about Slack is also that the conversation can continue outside of just the slotted time. So
yeah, great. Yeah.
Those goes pretty well, huh? So far.
Yeah, except that people don't ask questions.
Yeah.
I think everyone's just different right here with everything being so many people online.
I had one meeting with 1,000 people online, and then it was basically hopeless.
Is this the usual number now for NAC, about 100 people? Now there's 80, but typically I saw just over 100 in the morning in the first session.
It was, I think, 120 or so maximum.
Mm-hmm. Is that what you typically get in the face-to-face meetings as well?
I would say a bit more, Peter.
Zeg je wat?
I would say a little bit more.
Oh, okay.
It's about 220 in person on
Whoa.
average.
Yeah, yeah.
Because our ADAS meeting was reversed. We typically get 300. We had 600 in the virtual one.
The AAS was like that too. The AAS was huge. The replacement for the EWAS was huge last year.
Okay.
We'll have to see how it goes this year. So.
So I don't know. Maybe it's too cheap. Maybe we should charge people money, because then people also attend.
I think with very broad, general kind of discussions like this, people dip in and out, right? And that's just the way it will work, right? And a lot of people will.
Yeah, no, I mean that's very clear. It's like a customer society, so it's like a shop. If you like a talk, you go, and if you don't like a talk, you go away. Yeah.
Averaging about 20 to 30 people at one time on YouTube, with 111 total different people.
Okay, yeah.
0 seconds. They average 22 minutes and 24 seconds.
I mean, listen, you mean, but for example, if I have left its YouTube channel open all the time, so I average 2 hours or so, is that?
Yeah, you have a long average. So the average is down to 22.
Okay, Sven, the floor is yours. I'm going to start recording again.
Okay. So is Timothy Shimwell?
Yeah, I'm here.
Ah, there you are. Hello.
Hi. Should I share my screen or anything?
Yes, please.
Okay. Is that working all right?
Yeah, perfect.
Oh, perfect. Okay, well, ready when you are.
Well, it's time, so.
Okay. So I'm Timothy Shimwell. I'm here to present the LOFAR surveys, which is a project like some of the other projects that have been presented, done by a very large collaboration of people. We're now up to about 260 people in our collaboration. And really the work I'm presenting today is really the efforts of all of these people who are making invaluable technical or scientific contributions to the survey. This is just an image of a few of us, or one of our last group meetings a couple of years ago, actually, in Leiden, if you can recognize it. So just to outline a little bit what we're trying to do in the LOFAR surveys, is that we're not only trying to survey the sky with LOFAR, which I'll explain in a moment, but we're also trying to achieve a kind of coordinated scientific exploitation of the data, to ensure that really the surveys also have a very lasting and effective scientific impact. And for this, we've got a series of different scientific working groups, each are led by experts in their own fields. And through these working groups, we're hoping to make contributions to a lot of different fields of radio astronomy, but also some fields where maybe radio astronomy hasn't been playing that much of a role in the past, so maybe some new areas too. So firstly, what is LOFAR? Well, I'm sure everyone is a bit familiar with LOFAR, but LOFAR is a radio interferometer based in the Netherlands. It operates at very low frequencies, so it consists of two different types of antennas, which are shown here. The ones that look a bit like poles at the top are actually able to observe down to about 10 megahertz and up to 90 megahertz. And 10 megahertz here is actually the lowest frequency you can really observe from the ground. So this really allows us to explore a large range of the electromagnetic spectrum. The HBA allows us to go all the way up to 250 megahertz, which, while still very low frequency, is obviously a fair bit higher than 10 megahertz. And there's different problems when analyzing the different parts of the data. And LOFAR is centered in the Netherlands, in Exlu, in the north of the Netherlands. And it has baselines that span about 120 kilometers right across a large part of the Netherlands, or a part of the Netherlands. But the array is actually much, much larger than this and has been growing more in even recent years. The actual full array allows us about 2,000 kilometers of baselines. So what this means in terms of the properties of LOFAR is that we can actually, with the same data set, we can resolve arc-second structures whilst also being sensitive to degree scale structures all at the same time. And LOFAR is a very, very flexible instrument, so there's a lot of different ways that you can observe with it. But I'm just giving an example of an observation that one could conduct. And this is kind of the data we have to deal with when we're doing these LOFAR surveys projects. So in one 8-hour observation, we typically get about 13 square degrees of coverage. And across this 13 square degrees, we have 48 megahertz of bandwidth. And we get to about 0.1 millijansky per beam sensitivity. And I'll put this into context a little bit later, but at these low frequencies, this is very, very sensitive. But perhaps one of the most interesting things is what I touched on a minute ago. And if we want to image at 0.3 arc-second resolution with these data, from one 8-hour observation, we actually require about 15 billion pixels in an image. And this is about 10 terabytes of data. And to produce one of those images with so many billions of pixels actually is in the hundreds of thousands of core hours of processing just for one single image. And now to survey the whole sky, we require about 3,000 of these observations. So you can imagine the computational problem of doing this over the whole sky. So, but these properties of LOFAR make LOFAR an absolutely fantastic instrument for surveying the universe. And this is because it's got such a wide field of view coupled with the really high sensitivity. And to put this in comparison to other existing radio telescope surveys, these are kind of some really fantastic surveys from the past 20 years or so. You can see that LOFAR is really, the LOFAR surveys which are highlighted here in red are really probing a really new parameter space in terms of both sensitivity, and here the size of the markers are proportional to the resolution, so also in terms of resolution. And with the LOFAR surveys project, we're not just conducting one survey, but we're conducting a series of surveys to kind of both make things more manageable and also to exploit different aspects of the instrument. So we're conducting surveys at the lower frequencies, say around 50 megahertz, and these ones are called LOLs, and we do a wide survey here, and we do a deep survey here. And then we do ones around 150 megahertz, and these are called LOTs. And here again, we do a wide, where wide is approximately all northern sky, and we do a deep survey where deep is several hundred square degrees. And then we've kind of separated off the Dutch station surveys from the international station surveys, just because of the challenges in working with the international station data. So we have these surveys called ILOTS and ILOTS deep, which can actually use the same data as LOTS, data gathered at the same time, but have to be processed in a very different way, which maybe I'll talk a bit about later. So more qualitatively, what we aim to do from the surveys is here is basically the suite of images we wish to create. So in the top left, we have our surveys from the Dutch part of LOFAR. And this is about 6 arcsecond resolution at 150 megahertz. And obviously with lower frequency, the resolution gets worse. Then we can use the same data to image it up to about 0.3 arcsecond resolution images. And these are all real images from the survey data. We can also obviously do very much deeper integrations by just observing the same field for much longer, and detect much more sources in a field of view. So go about 5 or 6 times deeper in regions where there's a lot of scientific interest. We also, as I mentioned earlier, want to recover the very large scale emission as well as the very small scale emission. And this shows the capabilities. Again, this is kind of the same data set. This could be imaged at 0.3 arcsecond resolution, but this is a 6 arcsecond resolution image showing the emission we've recovered in this W3 star forming region, which spans about 3 by 3 degrees or something. And actually there's tens of millions of pixels within the emission of contiguous emission that we image here. And we want to do all of this at several different frequencies. So at the lowest frequencies, for example, 20 megahertz, right up to the highest frequencies that we want to observe, which is about 160, 170 megahertz. And also we want to do it in different polarizations, so we can study magnetic fields. And also we want the opportunity to look at the time dependence of signals. So there's a lot of different products that we want to create. So how far are we actually, oh, one more slide first. And whilst we want to do all of this stuff with LOFAR, which is really, this is a really ambitious project by just that, we also really want to exploit scientific synergies. Like if you have the radio data, we really need multi-wavelength data to help us with a lot of the interpretation, or data at different radio wavelengths even. So, for example, we have the Weave LOFAR follow-up survey starting soon, which is going to survey about 1 million LOFAR detective sources using the William Herschel telescope and the Weave instrument, which is being installed there. We also collaborate quite closely with eRosita and a little bit with Aperitif, which can also provide very complementary to help us interpret our radio images. But I think the main aspect here is probably the optical, just for the purpose of this talk. And this is because what we aim to do with the surveys is not just create our radio images, but this is, again, this is from our first data release. It actually shows what we've been able to do, which is take our radio images, and in this movie, the sources you'll see are the real radio sources in our survey, where the intensity is the brightness of the source, the size of the source is the actual shape of the radio source, and the redshift is the photometric redshift from all of the cross-matching efforts we've put through. And this is about 2% of the sky. And this is all real, all real radio sources, real distances. And it's really giving us a nice picture of the radio universe. And going out to quite high redshift as well. So this was a very large effort. And it just covers 2% of the sky. But this is all now public. This is all described in a few papers from 2019, which are linked to it at the bottom here. So how far are we about doing this over the entire northern sky and completing all of the aims of the LOFAR surveys? Well, I think this slide kind of summarizes the situation we're in at the moment. This is all of the data we've captured to date. So this is, in the top panel is the high band antenna data. So this is around 150 megahertz. And you can see in the background here is an image from a different telescope. It's a 400 megahertz image actually. But in the foreground, this the color scale shows the actual data we have with LOFAR, where the color scale reflects the sensitivity, the anticipated sensitivity of that particular region of the sky. And you can see we've surveyed about 60–70% of the sky, and we've got very deep integrations towards like about 10 different pointings or so now. And by very deep, I mean like, yeah, maybe less than 50 microjanskis per beam. With the LOFAR low band antenna, which is more like 50 megahertz, we've also surveyed a very large area. Here the sensitivity isn't so good, but because radio sources get brighter at lower frequencies, it's still quite sensitive to radio sources. And we also have some very deep observations there as well. And all of the LOFAR HBA data is gathered with the international stations so that we can image it at very high resolution, whereas the LBA data at the moment isn't done that. We haven't done that. This slide is deliberately quite full of text to highlight the effort that has gone into doing this. I'm not sure if you've seen many LOFAR talks in the past, but the LOFAR surveys have now been going for 8 years, and it's been an incredibly challenging project because LOFAR data, when it comes out of the telescope, looks like this image in the top right here. And to make this image in the top right, which is not really suitable for much science, into this image in the bottom right, took years and years of technical developments and also lots and lots of work on software algorithms to make them efficient enough to be able to do it in a decent amount of time. And this really intensive processing, to do this takes about 10,000 core hours for a Dutch-only image, but much, much longer for the international stations if you want to do it over a wide field of view. And we have 20 petabytes of data accumulated so far with the coverage I showed. So we're going to have even more data than that. So we really had to put an awful lot of effort into doing all the technical aspects of getting LOFAR and getting bulk data processing all up to speed. So we're now at a stage where we're really, I think, making very, very good progress with the surveys. And this is something we've been working on for the last couple of years. Here outlined in black is the area of the LOFAR surveys that we're intending to publicly release at the end of this year, or about the end of this year, with the exact timeline still to be determined. But this covers about 27% of the northern sky. It's got about 4.5 million radio sources. It was a huge project. It is actually 26 different observing proposals from LOFAR have contributed towards this. And it meets our specifications of about 1 millijansky per beam sensitivity. Just to show a few example images from it, it's very actually hard to display the images. So this is actually a noise map. And this is, yeah, showing we just get to about 100 microjanskys per beam. This is, you see regions where the sensitivity is much higher, and this is generally regions around bright sources. And at this sensitivity, typically 9 in 10 sources have never been detected before. So this is how new the LOFAR surveys are, in that 90% of our objects not necessarily new discoveries because the galaxies might be there in the optical, but new in the radio in terms of detections. So it's really pushing forward the whole radio window. This is just some example images, but I managed to make a little video earlier. So this is a little video which just shows us plan. This is the whole of the LOTS DR2 region, and I'll just play this. I'm a bit shoddy at moving the thing around, but this is now zooming in. You can see the coma cluster here, if you can recognize this. This is a giant radio relic in the coma cluster and a giant radio halo. Several famous galaxies are coming up in a minute. I think there's M101 or something. You can see all the extended emission. Actually, only about 9% of sources are extended at this resolution. In a minute, I'll zoom in and you can see actually more of a lot of the sources are just not there at the moment. Yeah, so they kind of come up now. All the faint star-forming galaxies are there. Yeah, and you can scroll around this for quite a long time, but I'll stop. I think there's a few more objects coming up. This is a galaxy cluster in the upper left. Yeah, and then there's lots and lots of stuff. But yeah, so this covers about 26% of the sky and is 4.5 million sources. And we do really aim to release this very soon. I'll just leave it to go to the last galaxies. Yeah, this is a nice galaxy cluster and a galaxy on the right as well. Yeah. And we've got lots more images too. So the images I showed were at 6 arcsecond resolution. This is exactly the same data, but here the sources have been subtracted to beat down the confusion noise, and this has been imaged at several arc-minute resolution. And here you can actually see the power of LOFAR in terms of the recovery of the very low surface brightness emission. This is galactic structures in this very, very extragalactic region that we've surveyed here. This is an absolutely spectacular map. I said earlier that we're doing polarization imaging. So this is taking the linear polarization and determining the rotation measures of these, and again, imaging at very, very low resolution. And this is showing, the different colors are showing different rotation measures. And this is showing structures in the interstellar medium at different rotation measures. So telling us about the magnetic field in our galaxy. This image in the top right is showing a little bit related to the previous one. This is again using rotation measures, but instead of sources within the galaxy, it's using extragalactic sources and looking at the rotation measures of those to try to probe the magnetic field in our galaxy. And this is different colors of different rotation measures here, and the red and blue will correspond to different structures in our galaxy. Yeah, obviously we detect far fewer sources in polarization, but still about 1 per square degree or so, so still a few thousand. Surprisingly, we actually also detect circularly polarized sources, which Harish Vedanthan will talk more about on next Tuesday, I believe. And we actually have about 100 detections of circularly polarized sources, including populations of stellar systems, which we've been really excited about recently. So, but one thing we're missing with the LOFAR surveys at the moment, the LOTS DR2, well, LOTS DR1, we managed to do this fantastic image where we went through the universe and saw all of the different redshifts of the sources. Now with LOTS DR2, we haven't yet been able to do this because we've surveyed such a large area of the sky. There is just so many different sources, and to match a radio source with an optical source is actually really quite difficult if the radio source has a very complicated morphology. So whilst we have several whole PhD topics dedicated to try to do this in an automated way, we've also set up a LOFAR Galaxy Zoo on the Zooniverse, where you can help us to classify and associate radio sources with each other. So for example, combine 2 lobes of a galaxy into one and find the counterpart. And then we can go and get all of the redshifts of these sources. And this will really help us both get the photometric redshifts, but also once we get the weave going on the William Herschel telescope, we can get spectroscopic measurements for these too. But we have an absolutely mammoth task. About 100,000 sources need to be classified in this way. So that was the LOFAR high band antenna survey. So that's around 150 megahertz. But we've also been making great progress at the lower frequencies. So at the lower frequencies, things are much more difficult. The ionosphere varies much more rapidly, And also the signal to noise is lower, so it's very hard to calibrate your data. However, we have recently managed our first, what we've called preliminary data release, because we want to get better quality of about 2% of the sky with the about 50 megahertz, and produced a catalog of about 25,000 sources, which is really nice. And this is all public and described in this paper linked to here. This is just a few example images from that paper. But I think perhaps the most exciting thing about the low band antenna is that we've struggled with this for years and years and years. I mean, LOFAR is now in its 16th cycle, where every cycle is 6 months. And this is work just from last year, really. And this shows the data we've managed to release. So this is on the left is now published and all available. But now using the same data and refined algorithms and refined techniques, we can actually produce the image on the right, which hits all of our specifications in terms of noise, resolution, and things like this, and really means that the 50 megahertz, we're really producing pioneering maps as well, which is really exciting. I mean, while 4 millijanskis are also fantastic, but 1 millijansky is much better, of course, and the fidelity is so much higher. There's also really exciting stuff that was recently done by Reinhard van Weren and Eric Ossinger and others in Leiden, which is imaging even lower frequencies. So here the ionosphere is really, really difficult. I mean, this is the lowest frequency you can observe from the Earth's surface. And this is maps of LOFAR at 20 megahertz. And this is actually this shows two things actually. Really nicely, it shows that we can make maps at 20 megahertz that have reasonable numbers of sources and things. But actually this cutout in the bottom right here is actually an international baseline resolution image at 18 megahertz of a very strong 3C source. So this is a really high resolution, well, the highest resolution we can do with a 2,000 kilometer baseline at 18 megahertz, and it's quite incredible. So now to go a little, sorry, I'm jumping around between all the surveys a bit because there's quite a lot that we've been doing, but this is now the deep surveys. So this is we have deep surveys at 150 megahertz and also 50 megahertz. And here we're targeting currently the most famous extragalactic fields in the sky. So we really recently published our first papers in this area. They're in this, they're basically all of the references shown here. And we published 3 of the most famous extragalactic fields. And what's really lovely here is that we can detect a peak source density of about 5,000 sources per square degree, which is comparable to kind of like the very deep VLA observations in terms of source density, but obviously we have a much larger area. And then we can, because these fields have such good auxiliary data, we can actually get host galaxy associations for about 97% of these sources. And also because of all the great data, we can get really good photometric redshifts because we're quite well constrained. And this allows us to do really nice things like this plot on the right here actually breaks down all of the sources that we've detected in these fields into different types of radio sources. And then you can obviously study their evolution and properties and things like this. So this is where most of this work is all published, but this one on the image on the right is in preparation still. This is just to show some images of this. So this is one of the fields, the most sensitive one, 20 microjanskis per beam noise. This is, I mean, probably about 100 times more sensitive than before these LOFAR surveys. And this is zooming in a bit, or zooming in a bit more, a little bit more, a little bit more. So this is about 5,000 sources per square degree here in the regions. We also have the same at the 50 megahertz. Again, as I explained previously, the 50 megahertz is much, much more challenging. But Wendy Williams in Leiden has done really fantastic work with this and managed to produce sub-millijansky images. This is of the Bootis field in this case. And here on the right is some source counts that Wendy's derived, so this is the radio source counts. And the flattening on the left here is basically where you start moving into a star-forming population as being your dominant sources in the map. And with the LOFAR LBA, we're now just about reaching that, which is really nice. So now perhaps one of the most exciting things in the survey, and this is work that a lot of people have contributed to, and Fritz Sveien, who's been sending all the emails about the NAC, is one of the key people here. And this is an absolutely fantastic image that he's made. This is the Lockman Hole field at 0.3 arcsecond resolution. And on the left is a really nice radio source, again at 0.3 arcsecond resolution. And here, so this map that Fritz has made is 7.4 billion pixels. So it's really, really difficult to display. So fortunately, there's a very nice poster type image of this where you can see some of the more spectacular sources. And I've also tried to make like a little movie of it as well, but it's quite difficult to even find the sources. So this is 6 arcsecond resolution on the left and 0.3 arcsecond resolution on the right. And I kind of just choose a few nice sources. So you can see, the new stuff you're learning by going to this resolution. And this is exactly the same data set, basically. I do try to highlight it in a minute, but it's not just spectacular sources that are detected. You can see the point-like sources are generally detected as well. Obviously, the surface brightness sensitivity is a little bit lower, but to compact sources and things, it's very, very sensitive. Yeah. So yeah, you can spend a long time doing this with these maps, but they're also facilitating a lot of science as well as just looking at nice pictures. So I'll just try to say, I mean, we now have actually 150 publications that have come from the LOFAR surveys, and it's very, very hard to summarize all of the different work that people have done. So I've tried to take a bit of a diverse range of stuff.
Tim, I have to tell you that your time is essentially up.
Okay, I'll just flick through. So we've discovered what we think is planets orbiting stars. We can map giant supernovas. We're trying to constrain dark matter annihilation. We can see really spectacular images of galaxy clusters on the right. We're detecting large populations of things like nearby galaxies, of course, and ram pressure stripping in galaxies. Obviously, very large populations of AGN. We're seeing some variable sources, which is really nice because low frequency variable sources is difficult. This is Hercules A at 0.2 arcsecond resolution. We don't quite resolve the black hole here, but it's quite high resolution for low frequencies. Many more studies. Probing magnetic fields in galaxy clusters or looking at particle acceleration. Trying to constrain the intergalactic magnetic field with polarization. Starting to do some cosmology with sky temperatures and 2-point correlation functions, exploiting synergies with all of these other instruments, like these are all papers that have made use of LOFAR plus another instrument. Yeah, so I'll leave it there. So we've done I've tried to summarize it in this slide. Thank you.
Thank you very much for your very nice talk. There's already 2 questions in the chat. So can you see them?
Let me try. No, I logged out of Slack actually.
No, here, the chat of the Zoom.
Oh, the chat here. Oh, no.
So there's a question from Kudkeken who asks, what fraction of lots sources is resolved?
Yes, it's always quite difficult to separate exactly the resolved from the extended emission, but we think about like 8.5% are resolved at 6 arcsecond resolution. But it depends a lot how you kind of make the separation.
And there's another one. What are the future planned surveys with LOFAR?
Yes, well, so with LOFAR, LOFAR is getting an upgrade in the next couple of years. And this is going to be an opportunity for us to reevaluate or evaluate again how to do pioneering surveys with the instrument to make sure it's really cutting edge. I mean, there's obvious capabilities in the long baselines and at the very lowest frequencies. So yeah, I think it remains to be decided what the future is after these surveys, but there's so much potential.
Another question?
Yeah, Tim, just a quick question. That was amazing image you showed of the galactic plane and just imaging these large like Cygnus loops and stuff like that. I was just wondering, how stable is the imaging pipeline in the galactic plane, and what's the plan there with doing galactic plane surveys?
Yeah, that's tricky. I mean, like, so this image that I showed earlier, like this this type of thing is obviously quite a distinct. This is in the galactic plane, but it's quite a distinct object. And so is the Cygnus loop. They're both, I think this one's a bit higher galactic latitude. And these are done in a completely automated way, where even the deconvolution of the millions of pixels is completely automated. But the like imaging the really diffuse stuff in the galactic plane and not these distinct objects, we need to test more. Yeah.
Yeah, amazing stuff, amazing image. Being able to recover all that structure. That's testament to LOFA's short baselines and long baselines.
And just for the last question about flagging, what fraction needs hand tuning?
Oh, the flagging is all, the flagging of the data due to radio interference or something is all completely automated. In terms of numbers, I think it's about 11% of the data that we lose in the when we observe in the high band. But I perhaps have to check that number. I think it's around that percentage. Don't quote me on that one. Yeah.
Okay, thank you. Moving on to the next speaker, with Sylvia Tonen. So I'm sending through the direct messages through the chat, like when you have 5 minutes left. So please keep an eye on that. So next speaker is Sylvia Tonen about stellar interactions and transients. So
Yes.
you could share your screen.
Wait. I'm sharing the wrong screen. I try that again. You want to share this screen?
No.
No?
Yeah, there we go. Yeah, now it is. Now it's fine. Oh,
okay.
Back to the previous one. Stop.
Exactly. So just to double
Perfect.
check, do you see one slide and one slide only?
Yes.
Okay, perfect. Yeah, so thanks, Sven. Yeah, so my name is Sylvia Tonen. And yeah, I want to thank the organizers for the opportunity to talk here today and to tell you a bit about the work that my new group in Amsterdam is interested in. And so what we work on is the evolution of stellar systems, how they interact, and what type of transients they give rise to. There we go. And so we often say, right, that stars are the fundamental building blocks of galaxies and of clusters. But it's also been known for quite some time that many of these stars are not single stars, they're in binaries. And the stars in these binaries, they evolve, they interact with one another, and every now and then they give rise to these bright transients that we love and observe. And the difficulty is that for many of the transients that we observe, we still don't know what their origins are. So for example, for gravitational wave sources, we know that these are mergers between black holes and neutron stars, right? But the big question is, how do you get black holes to be so close to each other that they can merge in the first place? And for supernova type 1a, the situation is actually much worse, because here we're still very much discussing even which stars are involved in the process. Now, despite these questions, I think this field is really, really interesting because a boom is starting to happen here. And that is mostly coming from a huge progress on the observational side. So to give you an example, currently we are observing about 3 supernovae every night with ZTF. I think that's already quite a high number. But in a few years, in 2024, when the Vera Rubin Observatory comes online, this number is going to go up to 1,000 supernovae every night, right? That is incredible. That's 3 orders of magnitude increase. It still blows my mind every time I think about it. And the consequence of that is that transients that we think of today as being rare, they will definitely not be rare anymore in just a few years. And that means that it's time for us to start looking into, those channels that maybe sound a little bit obscure, but we need them in just a few years. So I want to talk about some very novel evolutionary channels. And that is bringing me to talk about these types of systems. So not binaries, but triples. And I'll show you in a second that they are abundant, but let me say some other things about these sources first. And that is the type of triples that I'll be talking about. They look like this. So we have 2 stars in an orbit around one another, and then a 3rd star in a much wider orbit going around the center of mass of that inner binary. And these type of systems, they can be stable for very long times. So if that outer orbit is about 5 times wider or more, then these systems can be stable for Hubble times. And their evolution is very unique. So we know that that 3rd star can have a strong impact on the evolution of the inner binary, but the question is how and when and how often does that third star really matter? So triple evolution is something that we're really just starting to explore now. And later on in the talk, I want to show you those first results of what triples can do that binaries cannot. Now, I also promised to show you how abundant these systems are. Let me do that in the next slide. So what you see here is the binary fraction, the triple fraction, the quadruple fraction as a function of primary mass. And this is based on observations of very young systems, so before any interactions can take place. Now, if you focus on solar type stars, you'll see that the binary fraction is about 30% and the triple fraction is about 10%. So that roughly means that for every 4 binaries, one of them is a triple, right? So that's a decent percentage. But now if we go to massive stars, if you go to the right side of the plot, so O-type stars, then it's not that O-types are, we don't see them often as single stars. We even don't see them often as binaries, but the majority of the time they're triples and higher order multiples. So the importance of triples just goes up as we go to these more massive stars. Now, what I want to talk about today is triple evolution, how they evolve differently from binaries, just a little bit, and then I'll talk about the transients that triples and binaries can give rise to. In the end, I'll introduce you to a new channel to explain the origins of supernova type 1a. Okay, let's start with these triples. So let me start with an example of just one binary, and then we're gonna place a third star around it. So what you see here is the orbit, the semi-major axis of a binary as a function of time. And in this case, this orbit doesn't really do much. It's very wide, it doesn't interact. And the orbit just becomes a little bit wider as these stars lose a bit of mass in their stellar winds. Now, if I put a third star around it, this happens. The evolution is completely different. So what's the reason for this, right? What causes this divergence? Now, if you zoom in that moment in time, you see these huge variations in the eccentricity of the inner orbit. And that's a manifestation of the three-body dynamics. These cycles in eccentricity and inclination changes at the same rate, but those cycles are called Kozai-Lidov cycles. And we can get even more extreme behavior if you take into account higher order terms of the three-body dynamics, even so extreme that an inner binary can flip from prograde to retrograde. Now, if we go back to the example, then the reason why I like these high eccentricities is because this is when the stars get close to each other. So that's when, that's when all the interactions become strongest. So in this case, it leads to physical interaction between the stars, mass transfer. And that leads in this case to a common envelope phase such the orbit shrinks very drastically. Now a bit later, there's another mass transfer phase and eventually a merger. Now this system is interesting for a particular reason, and that is that what we see here is a merger between two massive white dwarfs. So this system actually is thought to give rise to a supernova type 1a. So I can take a binary that doesn't really do much and turn it into a supernova type 1a progenitor. And I think that's pretty cool. Now the criticism that I would give myself on this is that you can always come up with one example that does something interesting, right? The question is, how often does this really happen? Now, for that, we developed a code called TRAS to simulate the evolution of triples consistently, take into account stellar evolution, stellar interactions, but combine it with three-body dynamics. The code is publicly available, and of course I want to highlight all the people that are part of the TRAS team and that have contributed to the work that you're going to see in the next couple of slides. Now, we use this code to simulate a large population of triples and to just assess what is their typical evolution. Make different assumptions for their initial populations of triples. Now, what we found is that most of the time, there will be mass transfer in that inner binary. Now, that's about 2/3, 3/4 of all the triples. It's an interesting number by itself, but it means so much more if you compare it to what binaries do in that same mass range. because for those binaries, you'd only expect mass transfer in about 1/3 of all the cases. So it means that even though triples are 3 times less common than binaries, they interact 3 times more often, pretty much putting them on equal footing with binaries. So if you're interested in stellar interactions and what binaries can do and the type of transients, triples could be very interesting for you as well. Now, there's a couple more details that I want to mention, and that is very often when this mass transfer phase starts, the orbit is significantly eccentric. And that is something that clearly makes the triples different from the binaries, because this is not what we expect typically from binary evolution. There's a couple of more evolutionary channels that a triple can do, especially the orange, green, and the red ones are things that binaries cannot. I'd love to go, I'd love to talk about these things for an hour, but of course I don't have the time. So I'll just mention the green one, for example. This is where your third star donates mass to the inner binary. Pretty cool. Simon Poitry-Swart worked on that and showed that this can explain the formation of this very weird double blue straggler that is observed. And also the purple group I want to highlight, because these are the triples where there's no interaction, no mass transfer. These stars are just living their lives by themselves. And very interestingly, we found the first of such triples, in the Gaia DR2. So we found a resolved triple that contains 3 white dwarfs. So it's a nice confirmation that these triples can indeed survive for these long times, and also through all of that mass loss. Now, let's start talking about these transients that we can get. And this part of the talk, go back. Yeah, there we go. In this part of the talk, I always feel a bit like I've been trying to paint this beautiful picture of triple evolution, elegant theory, but the best thing is to destroy it all. So this is what we're going to do. And you've already seen an example of this, because this red category, those are triples that are very often are going to get destroyed. So these are triples that become dynamically unstable just because of their own internal evolution. And such instabilities lead to these kind of interactions. Let me try to start this movie. Yeah, here we go. So these are the type of interactions that we usually think about in the context of stellar clusters, right? And we see these beautiful trajectories of the stars that are definitely not Keplerian orbits anymore. And I'll just let you watch this for a second. Oh, there we go. And so in these interactions, most of the time, what happens is that the triple dissolves into a binary and a single star. But in some percent of these interactions, the stars get so close to each other that we actually get a collision between 2 stars. So this dynamical instability from our simulations, we find a galactic rate of about 1 event per 1,000 years, and about 10% of that leads to these collisions. Again, that's something that we typically only think about in the context of stellar clusters, so dense stellar environments, but with triples, you can also do it in the field. Now, I want to make a small comparison between collisions and stellar mergers. Because with collisions, I'm talking about stars that are being put on a collision course, so very high eccentricities, or even parabolic orbits. And for mergers in binaries, I'm thinking about systems that evolve on much longer time scales, where the orbits slowly decline, or where a star slowly evolves and starts overflowing its rush slope and transfers mass to its companion. And those kind of stellar mergers also give rise to transients that we observe, and that some of the audience members even work on. So the rate of these kind of events from observations is of the order of 0.1 event per year. So that's about 1,000 times more common or more frequent than the stellar collisions in the field. And the point I want to make is that this merger rate is actually so high that it implies that many of the single stars that we're seeing may actually come from stellar mergers. Now, this is something that Karel Tamik has looked into previously when he was doing his master's with me. Of course, now he's doing a PhD in Nijmegen with honor pols. And so Karel looked into the evolution of binaries, just binaries, no triples here. And he estimated from modeling the evolution of these sources that about 10 to 30% of single white dwarfs actually come from the merger of a binary, so 10 to 30%. And this is very relevant if you're interested in galactic archaeology, because if you use these stars or these white dwarfs to measure ages, and it turns out your white dwarfs actually come from a merger, then you may completely overestimate the typical age of that star. Now, this is everything that I wanted to say about these common evolutionary channels for triples, but there's many more evolutionary channels that are just, not as common as these ones. And I want to introduce you to one of them. And that one looks like this. It's very easy. We start with a triple with just 3 stars, massive stars. These stars evolve, turn into black holes. We just focus on those triples where we do get black holes, where the triple stays intact. And because of the mass loss and because of the supernova kicks, the triple enters a different dynamical regime. It becomes more like that movie that I showed. So the 3-body dynamics become more important, and we get larger eccentricity cycles in that inner binary, and eventually a merger of the 2 black holes in that inner binary. Now, why am I talking about binary black hole mergers? You guess it, gravitational waves. So the merger rate that we get from modeling the evolution of these triples is something like a few events per year per gigaparsec cubed. And it might even be a bit higher at low metallicity. Now, if you compare that to the observed gravitational wave rate from LIGO Virgo, then we get a rate, then it shows that this triple channel could give rise to a good fraction of all of those triples. Now, how are we going to recognize that one of these events actually comes from this channel? Well, we can do that in different ways. And one of them will be the eccentricities. This is what you can see on the plot on the right, that the eccentricities that we expect, so this is the eccentricity that you would measure from a source when it enters the LIGO band. And as you can see from this channel, the triples have significantly higher eccentricities than those of the binaries and the clusters. I do want to mention that these simulations from clusters, they are a couple of years old, and they don't include secular effects. And if you do what all the more recent works do, then you also find a higher eccentricity tail for the cluster sources. Now, other ways to differentiate this channel is by looking at the spins. These spins have a unique, or this triple channel gives rise to a unique distribution of spins that peaks around a chi effective of 1. Now, this is only one channel for these triples to give rise of gravitational wave sources, one that doesn't include mass transfer. And so that means that there is so much more parameter space for us to probe here. So stay tuned for that. And I just want to give you one more example of how these triples can be important, and that is for the mass spectrum. So what you see here is this famous plot of the masses of black holes and neutron stars as we've observed them in gravitational waves, as well as in electromagnetic studies. And what we expected before the LIGO Virgo observations was a gap between the neutron stars and the black hole, between the neutron stars and the black holes in their mass distribution, and also a lack of massive black holes, so the upper mass gap. But lo and behold, you start observing, and all of a sudden, we do see sources in that regime. So in the upper mass gap, as well as in the lower mass gap. Now, very often these high masses are then linked to clusters in which you can have multiple mergers of black holes. We show here that especially 170729 can be very well explained by multiple mergers in a triple. right? So if we have a triple, then first the inner two stars merge, and then this star merges with, this merger remnant merges with the outer star. And both the mass as well as the spins actually match the observed properties of 170729 very well. For the last 6 minutes of the talk before Sven kicks me off, I want to talk about supernova type 1a. So this is bringing me back to binaries. No more triples for the rest of the talk, just the binaries. And supernova type 1a are very interesting transients. They're one of the brightest transients that we see, and they're so useful in astronomy because we can use them to measure distances on cosmological scales. But one of the big problems with supernova type 1a is that we still don't know what their progenitors are, right? There's a consensus that a type 1a is a thermonuclear explosion of a white dwarf. But the big question is, how do you get this white dwarf to explode? That turns out not to be so easy. And so there's many channels that have been proposed to explain this. And the two classical ones that you see here, they rely on a white dwarf reaching the Chandrasekhar mass, either by accretion on the left or by a merger on the right. Now, these other channels, they are sometimes extensions on these models, mixes of these models. But the bottom line is that none of these models can explain all of the observed properties of supernova type 1a. This is, a curse and a good thing. We have so many observations that there's a lot of observational constraints, such as the spectra, the light curve, the range of energetics, the rates, and our model actually needs to lead to a successful ignition of a white dwarf. Now, I want to introduce very quickly a new channel for this that can actually explain all of these different properties, and not only can explain supernova type 1a, but also type 1a-like transients. So the nice thing here is that it gives a uniform picture of these transients. So this channel considers the merger of two white dwarfs where one white dwarf is a hybrid white dwarf. So this hybrid white dwarf, what is that? It's a white dwarf with a CO core but a very thick helium layer on top. So this layer can be as thick as 0.1 solar masses or up to 25% of its total mass. Now, how do you form these white dwarfs? Actually very easy and very common. So in a binary, if you strip a star, you end of its hydrogen envelope, you end up with a helium star. Most of those helium stars have a mass of about 0.47, and those will just naturally end up becoming such a hybrid white dwarf. Now, what we did is we made simulations of these mergers. And here you see a couple of cuts, timestamps of that simulation. So we assume that the lowest mass white dwarf gets completely disrupted. It forms an accretion disk around the white dwarf. Here you see that central object and then a cut through to the disk. We slowly start accreting matter on top of the white dwarf. It builds up a layer of material. And at some point that layer detonates. It sends a shock wave into the core of the white dwarf. And then there's a second detonation in the core of the white dwarf. Now, this scenario has been proposed before, it's nothing new. And also we've already realized many years ago that what really helps to set off that first detonation is if there's helium present in the system. Now, the only thing that our channel is adding here is that there's a natural way of having helium present in the system. Now, after this simulation, we fed it into a radiative transfer code to get spectra and light curves. Because of time, I don't have time to go into this plot in a lot of detail, but I'll just challenge you to try and find out which ones are the models and which ones are the observations, that's how much they are alike to one another. And this is only the second model ever that's able to reproduce these spectra and light curves. Also very quickly, I want to show you the spectra that we have of not a supernova type 1a, but a supernova type 1a-like, because we also match this variety of other transients, such as 2008 HA, but also calcium-rich transients, which is what you see here. And again, in red is our model, and it reproduces the observed features quite well. So what's different here is that it's not the hybrid that's disrupted, it's the hybrid that is actually the one that explodes. So my last slide before I go to the summary is this one. I want to make one notion about the rates of these sources, because all channels so far had a hard time to explain the high observed rates of supernova type 1a. So observationally, if the type 1a come from double white dwarf mergers, then 15% of all the double white dwarf mergers need to lead to a supernova type 1a. That's a significant fraction. Now, from modeling binary evolution, we showed that about 25 to 30% of double white dwarf mergers contain such a hybrid white dwarf. Now, we need to do more research to figure out which merger exactly can give rise to which transients, but at least here we have the potential of matching that observed rates. This is bringing me to my summary slides. And what I tried to show in this review talk is that I think the future is super bright for transients as well as stellar studies. And that was not a pun intended. Because there's so many observations coming. And that's really allowing us to go one level deeper to understand these sources, which is why I think it's now such an interesting time to look into these triples. So I showed you that they can indeed evolve very differently from binaries, how they can be dominant for some type of transients, such as collisions, and gravitational wave sources, of which they can be very important as well. I don't think that they will explain everything. We still need binaries as well. And for that, I talked about supernova type 1a, and I introduced you to a new channel that I'm really excited about, containing hybrid white dwarfs. And as the last slide, I just want to quickly advertise our Facebook group. If you're interested in triples or high order multiples, stellar system, planetary systems, supermassive black hole triples, any of this, then check out our Facebook group, become a member, and it would be really great to have an interactive community there.
Thank you very much. It was a great talk. Thank you.
Thanks.
Question, Harish.
Yeah, I had a question about some of the simulations of triples and their merger rates and their eventual evolution. How do these models agree with the rate of novae which we observe, and not supernovae, just novae, and the rate of companions we see around pulsars, because it's very hard to hide a companion around a pulsar. So
yeah.
Presumably that is extremely constraining.
It's a very good question. So the thing is that with triple evolution, we're still very much building up our understanding of their evolution. So the work that I showed here, it stops when the first phase of mass transfer happens, right? So we don't have the predictions yet for how many novae would come out of it or how many pulsars you would expect, but this is exactly the type of questions that we want to look into in the future.
Is this because it's very hard to model the dynamical effect of mass transfer?
It's for two reasons, right? So it depends on the type of mass transfer. If it's a common envelope phase, that's so complicated that we model it in a simple way, so that we can do. There is the issue that sometimes the orbits are still eccentric. That's a new, methodology that doesn't exist for binary, so that's something that needs to be tested more. And it's also a matter of not having codes available in the past that were able to model triple evolution. So now we just need the time to, do these calculations now that we have the code ready.
I thought I don't see you.
Thanks.
It is supposed to start at 5.
At 5, indeed.
It's 2 minutes more. Yeah.
Yeah, which still gives us 2 minutes. So.
Yeah. Can I ask a question?
Sure.
Sylvia, you indicate this Facebook page. This is I generally don't see this for researchers. Do you feel that your research that way is being more visible? Do you have any indicators for that?
So my main motivation for starting this Facebook group was to get more communication for this community, because triple evolution is such a new topic. Yeah. I just wanted a way, and especially now that we were organizing conferences, but we had to cancel them last year. This was a way to get, to form like a coherent community for the triples. So, the numbers that I can mention is that about 5 years ago, we had the first triple conference, and there were about 30 people. Now this year we had one that had, I think, over 100 people. And in the Facebook group, we currently have, I think, 220 members or something along those lines. So I think it's really nice to see, those numbers grow over time.
Thank you.
Filippo? Yes.
Yes, thanks for the very nice talk. I was curious about with these different channels for the 1A, what is your feeling about the usage for distance determination in general? What do you think that impact can be?
Can I
Sorry?
I want to double check that I understand the question correctly. Are you asking about the importance of knowing what the origins are of the type 1A for using?
Well, I'm wondering if the having different channels for the formation has an impact in our calibrations that we have for using the supernova as this standard candle, let's say.
Yeah. I think the difficult thing with supernova type 1A is that in some parameters, they are very uniform, and then in others not. And so we need to come up with something that matches all of that. And I think because of the uniformity, we have very long focused at finding one dominant channel. But it's clear that there's more channels and they will contribute as well. So with this channel that I'm proposing here, this would explain the bulk of the sources, but there's still enough room for the other channels that have been proposed previously to add in, for example, the manganese constraints, to just mention something. So I think what knowing the origin of the sources, okay, so currently in the studies that use supernova type 1A to measure distances, you already throw out the weird supernovae, right? You already do the picking there. But I think by knowing what the origins are, we can maybe do that picking, in a way involved by theory. So maybe we can improve upon that.
Thank you very much. I think this brings us to the end of our afternoon of invited talks and science talks in general. I would like to thank all the speakers of this afternoon for their wonderful talks. And now, perhaps Reinier, can you tell us what will happen now?
No, I mean, there will be a JWST web webinar, I think, and this can be started by Amina, I guess.
Yes, thank you.
Okay.
So I guess, welcome everybody to the third webcast of NOVA. I want to thank you for still being here, for joining us today after the first afternoon session of the NAC. Very nice talks by everybody. Congratulations to all. You might remember our last webcast was in January this year, just before the NOVA midterm took place. So I'm happy to report here that the review was very positive. So special thanks. So thanks to everybody, but especially to those that contributed actively to that review. And today we have our third webcast, and it's indeed focused on JWST and on MIRI, which is one of the instruments of JWST and one that has significant Dutch, especially NOVA component. Without further ado, I'd like to hand this over to Marieke Ban, who will chair the session.
Okay, thank you, Amina. So now we start with the program. We have indeed 3 speakers today who will talk about the Dutch contribution to the James Webb Space Telescope. They call it the Webb, by the way. After a few delays, the telescope is expected to be launched later this year on the 31st of October on a European rocket from Kourou. And the James Webb is a NASA ESA mission. And ESA's main contribution is one of the 3 instruments on the Webb, and that's the spectrometer and camera MIRI. But ESO is also involved in NEARSPEC, and Marijn Franks is a member of the ESA NEARSPEC science team. But in the next 25 minutes, we will zoom in on MIRI with contributions by the European co-PI of MIRI, that's Eline van Dishoek, the head of the NOVA Optical Infrared Group, Ramon Navarro, and the leader of the MIRI instrument team, Michael Müller. And they will talk about the science with MIRI, the Dutch contribution to the instrument, and the guaranteed observing time the Dutch astronomy community has acquired. And we will start with Ewine van Dishoek. So if you are ready, you can share your screen and take the floor.
Yes, good afternoon, everybody. Delighted to see you all on this late afternoon. As Amina already said, excellent talk so far at the NAC. And so hopefully we can keep you still awake for another 25 minutes. I'm going to talk to you a little bit about JWST MIRI, which is one of the NOVA instrumentation projects, but also, of course, very much at the heart of the NOVA networks. After many, many years, we are now nearing launch, hopefully later this year. Then by the middle of next year, hopefully start to do science. So just to remind you, JWST has 4 instruments on board. NearSpec was already mentioned with significant European and also Dutch involvements, actually built by Europe. But here we have the MIRI instrument, which is a joint partnership between the European Consortium and the US. And the Netherlands' contributions is in the spectrometer main optics. It's basically a combined spectrometer and imager. And the spectrometer is an integral field unit. And you will hear more from Ramon Navarro. He will actually show you that instrument in Dwingelo, at least a copy of it, in great detail. Now, before I continue, a big thanks to the entire MIRI team that built the instrument. This is just a fraction of them, but I want to highlight here especially Rieks Jager and also Bernard Brandel as the deputy PI, who both played an enormous role in the period that MIRI was built, so between, say, 2002 and 2012. And Jan-Willem Pel, who was instrumental in the design, and Gabi Cruz as one of the main engineers who actually worked on this. So big kudos to all of them. Now, why is JWST so popular and so interesting? It's because of the huge sensitivity gain. It's, of course, a 6-meter class telescopes in space. And so if you compare that with, say, the Hubble, and especially here in the infrared part, then you see that your gain is several orders of magnitude. You are now in the sort of tens of nano Jansky regime. At the longer wavelengths, the thermal emission from the sun shield, the telescopes start to pick up, but still, even there, we are significantly below Spitzer, which was, of course, a cooled telescope. Now, the same is here for spectroscopy, and just to compare with some of your other favorite instruments, again, you see here the 1 to 2 orders of magnitude gain compared with other instruments. And interestingly, ELT MATIS will have a similar comparable sensitivity, so will be great for follow-up of JWST sources, but at higher spectral resolution and spatial resolution. Of course, greatly hindered by the atmosphere, you can only see tiny parts around it. So why the infrared part? One region is probing into highly obscured regions, but ALMA can do so as well, radio can do so as well. So what is unique about the infrared? Well, it's really unique in quite a number of molecular and solid state features that are basically not accessible at any other wavelengths. Think of molecular hydrogen itself. Think of carbon dioxide, CO2. Think of the pHs, all the solid state features, ices, silicates. They are unique to the mid-infrared part of the spectrum. And that's why it's such an important wavelength range. But also, if you're not interested in all of these species, you're just interested in your typical optical diagnostics. By the time you get to a redshift of 6.6, all of those have shifted into the mid-infrared region. So that's another reason for going to the mid-infrared. So there's a huge discovery space in a quite poorly explored wavelength range still so far. Now, we actually are involved, the Netherlands, in many, many different projects, both the guaranteed time, the early release science, the GEO. In fact, the Netherlands has been hugely successful in the open time. I think according to statistics, we have 134 co-Is in the Netherlands on accepted proposals. So that is huge. And we're also leading at least a dozen of them. And they go across all the different topics, from high redshift galaxies to asteroids and PDRs. So let me just give you a taster of a few of these projects. This is the MIRI Deep Field, part of the Guaranteed Time program. We have very heavily involvement of Karine Caputi and Paul van der Werf. You see here the fields that is targeted, but when you observe with MIRI, you can also get in parallel with other instruments. And so you see that you can get at the same time, and this is a 60-hour very deep field, also very deep NIRCam fields and also near-IRIS fields. And the science theme is here really to study the buildup of the stellar mass, especially as that happens at a higher redshift. Where you really need the mid-infrared for all of these diagnostics, which have shifted into the mid-infrared, and also to really see whether your high redshift galaxies is young, true first light, that Massimo Stiavelli may talk about later in this conference, or whether you are basically looking at a more mature galaxy in which old stars have already formed, are already present. So that's a very exciting topic that will have a lot of involvement from actually all the four instruments. If we talk about stellar mass buildup, you can also go to galactic sources. Here we have a protostar. Protostars are very much obscured, so they are perfect targets for the mid-infrared. And also in nearby star-forming clouds, they have exactly the right size value match to the IFUs, about 0.2 arcsecond resolution. So you have about, say, 20 astronomical units resolution. And you can observe these many different components that used to be just a blur with Spitzer, that Spitzer beam, there was this whole region, but now you can really sort of get very nicely here, you see the footprint of MIRI on top of one of these outflows. And so again, the synergy also with ALMA sees the entrained outflow gas. With MIRI, you see the currently shocked gas, and you can really see sort of trace the launching mechanisms. For example, we now think that some of these are not the very collimated jets, but are the more broadly distributed disk winds that also play a very important role in the angular momentum transfer in disks, an increasingly important role. And again, MIRI will have excellent diagnostics in order to study all of these jets and winds and characterize their physics. Now, if you look at the same topic sources, then you can also look at the center, and there you see actually, you get your central spexels, and there you actually see an ice spectrum, and this is just to illustrate what is blocked from the ground, almost everything, especially that crucial fingerprint region between 5 and 10 microns, which is where all the complex organic molecules are. And this is really the big question is, are these comps made in ices, or are they actually formed in situ in gas phase? This is really where MIRI will excel in order to distinguish, for example, in comparison with laboratory data, whether you have alcohol or one of these other complex molecules. So also the Leiden laboratory is very much involved in here. And there are programs, both ERS led by Melissa McClure and also from the GTO. You can even go to spatially resolved. If you look at the edge on disks, say 80 degrees inclination, that you get the scattered light, the scattered stellar light, the scattered hot dust light, the scattered thermal emission, and you can now with MIRI do a spatially resolved. Again, you see the footprint here of these spectrometers. And so now you can really sort of dissect the different layers in a disk, layers that may have different ices, different compositions in planet forming regions actually that depend on whether you are on the ice lines or not. You can also look at the disk phase on, and this is a large program that is actually co-led by Inga Kamp, where you now are probing the gas in the inner disk in emission, the hot gas in emission, that will actually become part of the gas that builds giant planets in these regions. And so here again, you see the incredibly rich spectrum that we expect to see there with MIRI. Finally, then the exoplanet atmospheres, and I'll stop here, is another region. These are the more mature exoplanets, where you actually see that, especially here in this mid-infrared range, you can actually distinguish different models for exoplanet atmospheres, for example, with or without thermal inversion. You see that that is the crucial wavelength range. Also, at the longer wavelengths, you're more sensitive for the cool super-Earth. Michiel Min, Rens Waters, Inga Kamp are again very much involved in this research in the GTO, but also the GEO, Jean-Michel Dessert as well. And you see here not just the molecules, but also here the solids, the different silicates that actually are seen, especially here in this long wavelength region. Now, thanks to the different programs, quite a different variety of exoplanets will be probed by the various instruments, including one of the TRAPPIST ones in the DTO time and others in other programs. So by the end of the first cycle, there will already be a very rich and diverse database on exoplanet atmospheres, which will be very good. And finally, just to end with, you can do this also time resolved, and you can look at the weather on exoplanets by looking at how the spectra change when you go from the ingress to the egress. And see here, for example, the morning and evening clouds that could form on a hot Jupiter. Very nice work by Michiel Min. So to end, you will hear a little bit more about the instrumentation. You'll hear a little bit more about the software. And then here in the networks, this is where we do the simulations, write the proposals, and get the time. So we are really very excited to get going soon with MIRI. Thank you very much.
Thank you, Evine, for this very interesting talk. We move on now to Ramon Navarro, and he will talk about the NOVA contribution to MIRI, which was delivered, correct me if I'm wrong, back in 2009?
2009, yes.
He will give a live demonstration. So I have a question to the host of this Zoom to spotlight him, because he will give a live demonstration of the web scale model, the MIRI thermal vacuum model, and the MIRI mirror. So Ramon, the floor is yours.
Thank you so much. And Evine, it was really interesting to see all the plans that the scientists have with MIRI and with the James Webb Space Telescope, and it's very exciting. And we're really looking forward to using the telescope, of course. Welcome. We are now in Dwingelo, in the central hall of NOVA and Astron, and I'd like to show you both the James Webb Space Telescope and MIRI, but we start with the James Webb Space Telescope, and I'll tell you a bit about this. So this model has been created by our colleagues at NOVA and Astron, and the first thing that strikes is the gigantic 6.5 meter mirror, which is made of 18 segments. It's all beryllium, extreme lightweight material, gold coated for enhanced reflection. The second thing that you see of this James Webb Space Telescope is a huge sun shield. It's 21 meters by 14 meters in size, and just by the sun shield, the telescope is passively cooled to 50 Kelvin. The sun shield is way too big, and the telescope as well, to be launched in this configuration. So during launch, everything has to be folded to fit in a 4.5 meter diameter because it has to fit in the fairing. And then with this Ariane rocket, it will be launched from Kourou and directly into a transfer orbit towards L2. And this is Lagrange point 2 of the Earth-Sun system, which means that the Sun, the Earth, and the Moon are all on this side of the telescope. And the telescope can peer into the universe undisturbed for that thermal radiation. It also means that if I rotate this, this side of the telescope, of the spacecraft, which is the bus, is in communication with Earth. And there's also a solar panel over here. And because of the huge sun shield, there's some solar radiation pressure on it. There's this tab that you can see, which is the trim tab, to be able to steer the telescope in a very energy efficient way. And now we have come to the back of the telescope, which is the ISIM module. And I want to present what is inside. Inside is the 4 different science instruments that already described. Most prominent in this picture is MIRI, and I want to show how it works. If this works. So this is the MIRI optical configuration map. It shows the detector, and it shows, if it works. Yep. This is the size of the imager area, and there's plenty of different filters. This filter wheel has been developed by MPIA in Heidelberg. There's also 4 different coronagraphs, 4-quadrant phase mask, and a LEO stop. There is a low resolution spectrometer that creates a spectrum from 5 to 10 microns with a resolution of about 100. And barely visible in this graph, but very important, is this part over here, which is a medium resolution spectrometer. When you put a bunch of galaxies in the field, it will be sent to 4 different spectrographs in integral field mode. And it works like this. The light from the telescope is actually split by means of dichroics into 4 different wavelength channels. And these 4 different channels are sent to integral field units. And over here you have to notice that these dichroics are actually placed on rotating wheels. And I'll come back to that in a second. The integral field units uses sliced mirror arrays to slice the image into a thin stripe and put them end to end in order to easily make a spectrum. Then the light is sent from the integral field units towards the spectrometer. And this is the part that has been developed by NOVA and Astron. And here the light is collimated, sent to a grating for dispersion, and then put on the camera for detection with the detector. Please note that the dispersion is done by grating wheels, and they're actually on the very same axis as the dichroic wheel. So very cleverly, if you select different dichroics for different wavelengths, you also select the corresponding gratings for dispersion. And this is then the image that you will get on the detector, and very cleverly, 2 spectrographs use only 1 detector to detect the spectra. And we have come to MIRI over here. This is the thermal vacuum model. And actually this is the place where the detector is located. And if I will illuminate some lights over here in the area where the input of the light is, you will see them reflected or end up as spectra on the detector. Also in this model, you can see one of the rotating grating elements over here. Actually, on the location of these grating elements, we now have 2 mirrors to be able to test this whole this instrument. And when I rotate, you can see and peer inside and see the different mirrors. Such a mirror module is about 0.5 meter in size, and the operating temperature is 6.8 kelvins. And MIRI will actually, this SMO box, spectrometer main optics, will shrink by about 0.5 millimeter and still be able to work correctly. The central structure is made from a solid aluminum block of about 220 kilograms, and it has been milled down to 1.5 kilograms, but still strong enough to survive the heavy vibrations during launch. What I have over here is one of the mirrors that is used inside, and these mirrors have been made by single point diamond turning. So a single diamond has shaped this entire surface to nanometer accuracy, and then it's gold coated to optimize the reflectivity. So this is the tour of the MIRI thermal vacuum model, the James Webb Space Telescope, and I hand it back to Migo, who will tell about software and the capabilities and the calibration of the system.
Are you ready, Migo? I am. Let me share my screen. This is the last talk in this web special. And talking is Migo Müller about the MIRI science team, instrument science team. Excellent, thank you. So after building the instrument, of course, we're not done. That was the first part of the investment. Now we spent quite some time testing and calibrating it. And the next part is going to be reaping the benefits, which is why we're doing all of this. I'm going to get there in my last slide. Let me emphasize that after the engineers, mostly at Astron and elsewhere, have built it, testing and calibrating the instrument is now mostly up to scientists. So we speak the same language as you guys here.
So we here in the Netherlands, we are an integral part of the test and calibration team. And the biggest calibration contribution we do is on the MRS fringes. And I'm going to be talking about that in a couple slides. We have done a few test campaigns. I'm going to briefly mention them here. They were at Goddard Space Flight Center, 3 of them, cryovacuum 1, 2, 3. Then the OTIS, that's a nice acronym. At Johnson Space Flight Center, that's me here in front of the big bay, behind which is the vacuum chamber, the cold vacuum chamber that housed James Webb, or the telescope and the instrument science instruments at the time. Exciting live telemetry, temperatures going down in real time. Here's my part of a live demo. This is all the various RSA tokens you get to play with. A badge you can flip and show at various doors. It's, let's say, interesting. What we're now gearing up to, and that's the next big exciting part, is commissioning. That is the first 6 months after launch. And let me remind you, launch is foreseen by the end of October this year. So this is getting very real now. And after commissioning, once we've checked all the boxes, which we hope we will do in 6 months' time, but of course that isn't deterministic. If it were deterministic, there were no point in commissioning. Then will be the routine science, the exciting part. But yeah, as we do all this, as we test and check out things, we gain instrument knowledge. And the most important part for our team in the Netherlands is the fringes in the MRS. So here on the right is what you would hope the detector would look like if you flash flooded, all the different slices filled with light. But in reality, we have these, well, fringes. You really see them in the detector image. And in the extracted spectra, they look more like this. So we see the signal that we measure goes up and down. There are periodic modulations in the sensitivity. And if you've ever done highly resolved spectroscopy, you know them. You have standing waves within the optical path, Fabry-Perot type resonator. In the case of MIRI, it turns out the resonating cavity is actually the detector substrate itself. So within the detector, it's a couple of micrometers, so at the length of our wavelengths, we see 1 or 2 different fringes that then can beat with one another, and we get these interesting patterns that we need to get rid of in the pipeline so you can make sense of your data. And that's what we do. In the pipeline, what we do is we have a 2-step approach. We first divide by a static fringe flat, and that does most of the job. So we go from this black, nasty signal down to the red, which is a lot better, but still has some clearly visible residual fringes in it. And we then fit that semi-empirically by fitting sinusoids and up a number of them. And I could talk for hours about the details, but I don't have the time for that. And this is how we go from red to green. And this is an old picture. In real life, for short wavelength data, we can now go down, correct for fringes, down to the noise level in the data. So short means up to like 10 microns or thereabouts, up to channel 2B. So we're doing really well on that front, at least in the extracted spectra of point sources, and of course in fully extended sources, of which there aren't many on the sky. Semi-extended sources are more complicated, and we're working on that. For the longer wavelengths, we had a problem because there we had these 2 fringes beating with one another, and that made our life harder. And I believe we now have that under control, and I don't have good plots to show that, but just take my word for it. We're now busy validating that, but we should be as good as in the short wavelength. So everything should be under control. And by the time we're in space, you should be able to see any sort of features you want down to the 1 or 2% level or so. And you do need that for some of the solid state features. But really, while we're doing all this is, all this testing, if you do our job well, you don't hear much about it. But we do build up expertise in this country. And this is a resource you people can tap in. And this is part of our job description, to help scientists, and we're doing that. We've done it for the first round of general observer proposals, GO. We've had this workshop, and you've probably heard about it if you care for James Webb at all. And we just heard these impressive figures from Evina, how many co-Is in this country had been involved in successful programs. I know of 8 PIs. This is definitely putting this country on the map. I would argue we're punching above our weight, and that's a good thing. I would argue this is NOVA's investment paying off in real life. We'll get all this data. So if you need any help with the data and how to make sense of them, feel free to contact us. And I have my email address down here. There's more, it's so stripy. There's more people in the team. And of course, this was the first round for proposals. There will be more, probably once a year. And we're launching with a requirement of 5 years lifetime, but with fuel for 10. That's all I can say. Thank you.
Thank you, Migo, for this wonderful talk. Now it's time for questions. I think Jacqueline Quist has kept an eye on the chat. Are there any questions in the chat, Jacqueline? There were no questions yet, only a compliment by Bernard following. He says it's an impressive concept and demo. So I wanted to share that with you as well, of course. Okay. Are there any questions? No, no questions here. No. You can talk, you can say your name. Now, the presentations were all very clear and informative. Listen, wants to we have a question. Yeah, go ahead.
Wow. Sorry, it wasn't a question. I just wanted to say that we had in the cycle 1 proposal we had 10 PI proposals that were accepted, 7 co-PI proposals, and 134 co-I proposals. So the Netherlands is doing pretty well.
Didn't catch them all.
Thank you, Melissa. I see a raised hand. Go ahead.
Hello. Thank you for the very nice talk. When you showed the spectrum for MIRI, where you have shown how you have corrected for the fringes, it appeared as if there was a long-term pattern in the spectrum, as if there was a longer wavelength modulation in the spectrum. Is that correct, or am I just looking into it a bit too much?
No, you're right. And this is, I was showing you old data there. This is using the old fringe flat, where we did not use, where we only fitted a single fringe model to the data. In reality, we have 2 and they beat with one another. And this beating gives you this somewhat smooth, long periodicity thing that she actually detected. Very good. Took us a while to appreciate that, and the harder part to actually fit it to the data, but that is under control now.
Thank you.
More questions?
Actually, I have a question about the Fabry-Perot interference pattern correction. So I see you use a kind of empirical way to correct it with sinus fitting. Isn't there like a way to calculate the optical function of the Fabry-Perot and taking into account the difference of illumination to have a more physical correction?
Oh, absolutely, absolutely. And this is how we derive this the first step, the fringe flat.
That's the first step.
Yeah, I didn't.
So the residual are due to difference of illumination or to difference of understanding of the coating itself that gives the Fabry-Perot reflection?
So there's a couple of things. There's the thickness of the detector and the optical thickness of it. That gives us the principal fringes. So we fit the Airy function for that. But then it's somewhat, that is easy to calculate for well-collimated monochromatic light. Yeah. But in a pixel, we have some distribution of incidence angles, and we have some distribution of wavelengths. And this leads to some smearing out, and that makes our life harder, especially for point sources, the collimation angle changes a bit if you're on source or somewhat off source in the wings of the point spread function, things like that. So there's limits how far we can go with the analytic model.
And this is why we keep the residuals that we then later fit away with sinusoids.
Okay, thank you. I remember for SWS, we had some problem of fringes as well. Remind the history. Yeah.
Yeah, should probably have added all our code here has a long heritage down from ISO days. It was used for Spitzer and Herschel. So over the decades, I should say, we've built up quite some heritage that we're now putting to use for MIRI.
Yeah, thank you, excellent.
Okay, thank you. I think we have time, Jacqueline, for one more question. Absolutely. So raise your hand or write it in the chat if you have a question to one of the three speakers. And if not,
it's been a long day, of course, for everybody. It's been a long day for everybody.
Yeah, I think so. So we're wrapping up now. Thanks all for joining. I want to thank the speakers again, and also the NAC, of course, for hosting this third NOVA webcast. The webcast will be hopefully online in the coming days on the NOVA Astronomy website. And the next NOVA webcast will be right after the summer in September. See you then.
Bye-bye. Thank you.
Bye.